All right, Ilda, may I start or not yet?
Yes, we can start now.
I should try to have my slides. Maybe.
Okay, so try first.
I should be let to share screen.
Yeah. Okay.
Am I allowed? Okay. Maybe that's it. Can you see?
Yes.
Very good. Okay.
All right. So maybe let me explain that I'm not the chair of this session. Professor Józef Przytycki is, but he's also the first speaker, and I guess the Pauli exclusion principle prevents him from introducing himself. So hence I have the honor. Józef is a friend to many, and some of you know him at least in the reduced form, that is his name, namely as the letter P, the first letter of his name, which is part of the famous Homlet PT, not polynomials. Let me hear this. So Józef Przytycki, and I hope I impressed you with my ability to pronounce his name, is a professor of mathematics working at George Washington University in Washington from 1995. He obtained his PhD at Columbia University in '81. And before joining the Washington University, he was a professor in many places, including the University of British Columbia, University of Toronto, Warsaw University, and University of California at Berkeley. He was also a member of the Institute for Advanced Study in Princeton. He's an editor of 3 mathematical research journals and published more than 150 research papers in refereed journals and 3 research books. He's finishing his next book for Springer, written together with his PhD students. He also wrote 10 papers on history of mathematics and on mathematics for school children. He was invited to speak at numerous conferences at universities throughout Europe, Canada, China, India, Israel, Japan, Korea, Mexico, and of course, United States. Currently, he is a principal investigator for the Simons Collaboration Grant for Mathematicians. He is a fellow of the Washington Academy of Science and co-organizer of the series of international conferences. The best known is perhaps the Notes in Washington. There were already 49 of them, and also Notes in Poland, and also Notes in Hellas. He graduated 14 PhD students. And most of all, he's a fantastic presenter, and I'm sure you will enjoy his talk. Józef, the screen is yours.
Thank you, and I hope you can see screen. And it's my great pleasure to participate in this conference for Zbyszek Osiewicz. And I'm very glad that it was organized. So I would like to thank organizing Hilden and Jesus. And I'm very happy to give this talk in memoriam of Zbigniew Osiewicz. And Jurek point out that I have 150 pages. So I promise that I will finish on time as long as I will be reminded by Jurek. Because the first pages are very important because it is dedicated to Zbigniew. Then I talk about my work and creation of scale modules and algebras. And I think this is part of big project of Zbyszek. I will talk about this more, so maybe I should not say too much before. First, you see, I'm also faculty of University of Gdańsk, try to spread my knowledge in Poland, but of course, George Washington University is my main employer. Okay, so this is George Washington University. Many of you know, especially if you attended Notes in Washington. But George Washington University is just between White House and Watergate. And I think is the proper position for my university. I think we are proudly can be something between White House and Watergate. Okay, Potomac is here. There's a river Potomac. This river is called Watergate. Okay, So this symbol maybe Zbyszek would like. I often start my talks from this symbol. This is all knot theory and graph theory together, symbolically. And you combine these diagrams together and get reasonable theories. Okay, so because I will talk about scale module, I wrote scale modules is perfectly fit in broad idea which Zbyszek was developing, meaning applied category theory. And here is more about scale modules, and because they cover the last 100 pages of my talk, so maybe I will be unable to mention them at all. So what are scale modules? We have, in narrow sense, I would say, but we have knots in three-dimensional manifold, and we try to manipulate of them. And the simplest manipulation is to introduce some relations, some linear relations. I would prefer to have loop relations, and in fact, I was trying. Maybe not loop, but quandle, but anyway, some quasi-group with some properties. But anyway, they have some properties, and we glue these pictures and make linear relation between them. So I take module of all links in three-dimensional manifold and define by this linear relation. This is more or less scale modules. This is module at not loop or quandle or something like this. And there's plenty of possible choices, whatever pictures we choose. So I wanted to try favorite pictures of Zbyszek, but there's some tradition what we choose. However, anyway, there's crossers or crossing or maxima and minima, etc. So there are nice pictures. So how we choose this relation, we are motivated, of course, by what is known. And here I have even home flipped, which Jurek was trying to say with capital letters. I can try to say who are these people, but maybe later, except of course P, because Jurek already mentioned. So there are various old Alexander and new polynomial invariants of links in classical S3, and scale modules are, in a sense, natural generalization of them. So we like to say about quantum links, but it is just abuse of language. Maybe Q links would be better. Okay, let's go. So for physicists, I should mention that recently, or maybe already 15 years ago, Edward Witten took great interest in John's polynomial, then its generalization Hovanov homology, and finally, last 3 years, in exactly my scale modules. And he posed a very interesting conjecture. So I will tell about this conjecture a moment, but namely, Witten was interesting. What is the structure? He wanted scale modules to be finitely generated, and they are not. But he wanted to make from them topological quantum field theory. And one of the axioms, I think, unneeded but useful, is that it's finitely dimensional. So he conjectured that maybe Kaufman bracket scale module is very often infinitely generated, but maybe it's three-part, or maybe if it is taken over the link of rational functions, it is finitely generated. And I never heard Witten talking about this, but I heard third hand. And when I heard this conjecture, I said, I know plenty of counterexamples. And then all this infinitely generated scale model I was testing, and no, over a link of rational functions, miraculously, they happen to be finitely generated. So it is great conjecture. And I was then supporting this, and it was solved using very nice tool for various discipline of mathematics, mostly algebraic geometry, but not only representation, etc., by Ganningham, Jordan, and Safronov. I wanted to say that I will talk about this, but it's on the page 147. So who knows? But conjecture is solved. There are generalization of this conjecture, and for one of them, my student found counterexample. So Witten was right, his students not always. So now, historical perspective, more historical perspective. I was claiming that Zbyszek is kind of in the tradition of symbolic mathematics, but old tradition. So starting from Leibniz, and for us, most important is Eilenberg from Warsaw. Okay, first Leibniz. So this is a story which probably everybody knows, but especially the second page, which I'll show in a moment, is worth of remembering. So in the letter to Christian Huygens, in 1679, he wrote, "I am not content with algebra in that it yields neither the shortest proofs nor the most beautiful constructions of geometry. Consequently, in view of this, I consider that we need yet another kind of analysis, geometric of linear, which deals directly with position as algebra deals with magnitude." We can say that he's talking about topology, but no, I think he's talking about everything because just the beginning, there's plenty of branching. He's talking about graph theory on low level, about topology on higher level, but clearly about category on higher level. And this is the second citation from the same year, when it is more clearly said by Leibniz. So this is not Leibniz, though, this is comment. As far as back as 1679, Leibniz, in his Characteristica Geometrica, tried to formulate basic geometric properties of geometrical figures, to use special symbols to represent them, special symbols, and to combine these properties under operation so as to produce others. He called this study analysis situs or geometria situs. Clearly, it is category theory. So as we know, our conference is applied category theory, and category theory was already kind of predicted by Leibniz, and in fact, Eilenberg, so I should probably say a few words about Eilenberg, because in Poland we know everything. And there's a very nice article by Stefan Jackowski about Eilenberg, early years of Eilenberg in Poland. But really, advanced category theory started from 1942, when Eilenberg was able to escape from Poland. I mean, he left Poland a few months before the war. So I think about Eilenberg as the primary student of Leibniz, but student in the capital letters. And of course, we know Eilenberg has many co-authors, and he was very kind of active, and listening to people. MacLean was very important, but there were many others. And in fact, Stefan Jackowski in his article claimed that already kind of elements of category theory was before Eilenberg left Poland, but we can say it was already in Leibniz writings as well. So I was thinking about Zbyszek Oziewicz as person in the line to this. Eilenberg, student of Leibniz, Zbyszek, student of Eilenberg. I am not sure they ever met, but maybe. Okay, so a lot of people talk about Zbyszek already. So I just put his early life just to have one transparency about his life. I think we had many stories, so I will comment only about these early things. So yeah, as you see, he was a young child when he had to live with his parents in Vilnius, and family settled in Wrocław. So he did master's degree from Petersburg, and there's plenty of anecdotes about his stay in Petersburg. But here at conference, several people mentioned how Zbyszek, who is very nice and quiet, and maybe not quiet, but nice person, was very often stopping people for giving presentation and asking questions, not letting, especially students were very scared of him. So I think he brought this from Leningrad, because this is tradition of Russian School of Mathematics. I heard talks stopped by Novikov, Fields medalist. He didn't let the speaker to go further than first definition. So Zbyszek was not that bad, but he was in this tradition. But he was well-meaning. He was not mean. However, some students were afraid of him. One of my students really was afraid of him. Okay. So now finally we go to closer to my topic. However, I will make various digressions. So revolution in knot theory and putting knot theory in general setting is discovery of Jones, of his polynomial invariant of knots. So knot theory before Jones, or maybe before Thurston, another Fields medalist slightly earlier, was really thought to be part of algebraic topology. And the main American knot theoretist, Ralph Fox, was stressing this, that what is really knot theory? We have to use properly fundamental group, homology groups of coverings, so coverings, homology group, branch cover, maybe more sophisticated algebraic topology tools. But all this, first of all, was not so sure when Thurston came, because he said geometric structures on knot complements are important. So you have to incorporate some geometry. It is very useful, and Thurston showed how useful it is. But really with Jones, because Jones' polynomial was not like old polynomials, like Alexander polynomial, which can be derived from fundamental group from universal cover or from other algebraic objects related to knot theory. But till now, there's no good interpretation of Jones' polynomial using a fundamental group or related things or coverings. Rather, Jones' polynomial is close to object of statistical mechanics. And in fact, Lou Kaufman very quickly after 84, maybe in 85, noticed that really Jones' polynomial, more or less, maybe one variable is lost, can be taught as state sum in Potts model or some variation of Ising model, but really state sum of Potts model. But here, when I was listening to talks today, there's another question. Potts model is really given kind of special, the Ising model, which is solved, planar one, is on the plane. Looks like we look for diagrams. And Jones' polynomial has nice definition using braids and von Neumann algebra, but the simpler definition I will show in a moment is really diagrammatic. So in fact, part of the reason I divided scale models, and this very well fit what Zbyszek will say, is to have coordinate-free definition of Jones' polynomial. But of course, if you generalize, you better do in any three-dimensional manifold, then you don't have even projection. So you have to do different approach to Jones' polynomial and its generalization. So some technical things, some of this no, but not to be too technical, I copied from Jones when he wrote about his discovery. So he wrote about his discovery as this. It was a warm spring morning in May 1984 when I took the uptown subway to Columbia University to meet with John S. Bierman, a specialist in the theory of braids. I should add, Bierman was my PhD advisor at Columbia. In my work, so this again, Jones, in my work on von Neumann algebras, I had been astonished to discover expressions that bore a strong resemblance to the algebraic expression of certain topological relation among braids. I should comment that in modern language, Jones didn't know about this. This algebra, which really he was kind of getting, is temporal-leap algebra, another algebra very important in physics. Both Temper and Leap are very well-known theoretical physicists. Okay, let's go with Jones. I was hoping that the technique I had been using would prove valuable in knot theory. Maybe I can even deduce some new facts about the Alexander polynomial. I went home somehow depressed after a long day of discussion with Bierman. I did not seem that my ideas were at all relevant to the Alexander polynomial or to anything else in knot theory. But one night, the following week, I found myself sitting up in bed and running off to do a few calculations. Success came with a much simpler approach than the one I had been trying. I realized, you don't see this, but I realized that he discovered the really new invariant of knots. So first, how he knew that there's new invariant, because his polynomial, now Jones' polynomial, was distinguishing the simplest trefoil knot from its mirror image. Alexander polynomial is not doing this. But I think on philosophical level, there's much bigger difference. Alexander polynomial can be computed in polynomial time. It is really determinant of some big matrix, which can be found using Alexander matrix, Fox-Alexander matrix, which will be computed from diagram. But it's matrix of size related to the size of a knot. On the other hand, Jones' polynomial, it is proven computing this at NP hard. So up to famous conjecture, it has no polynomial grow algorithm. And I think ideologically, it is the biggest difference. If I have time, after my 150 pages, I will tell a few words about my trying to compute parts of Chowanov homology, not on the Jones polynomial in polynomial time. Generally impossible because we think impossible because NP hard. Okay, so now further with Jones. Still in May of 1984, or this is me. In 94, he was trying value substitution to the variable t in John's polynomial. And he found that for t equal -1, it is the same result as for Alexander polynomial. So at least this polynomial is, he knew only that it discovered a mirror image of Treffer, but he was doing initial calculation by hand. So he knows that it's related with alt invariant, but it's definitely something new. So this invariant for t equal -1 is now called just determinant. In fact, it's pretty related with graph theory determinant, or complexity of networks by Kerckhoff. Okay, so finally, the John's polynomial. So normalized for trivial notice 1, L plus, L minus, and L0 are three diagrams which are locally the same, so kind of algebraic symbols. So it is what really Zbyszek was trying to do, except we should have the symbols in context. They are not abstract symbols, but they are embedded here on the plane and generally in three-dimensional manifold, but here on the plane. So let's go further, because without picture, it is not worth anything. So this is John's polynomial is using the same picture, but it has very special value. But generally, and this is kind of discovery, really Jones probably knew already about this, but Jones was a very nice person who was telling around. So we have the 6 teams of people who discovered generalized Jones polynomial, now called home-flipped polynomial. So we use these 3 pictures. In home-flipped polynomial case, they are oriented, and then we put among them linear relation. But not abstractly, but this picture embedded on the plane in this case, and outside of this picture, they are exactly the same. We don't have linear relation to abstract picture. It depends on their position. So, and home-flipped polynomial have no restriction, any coefficient works. Then came Lou Kaufman. I already said that it was Lou Kaufman who first found decisive connection between John's polynomial and statistical mechanics. He showed that really John's polynomial is really state sum of some physical things. Potts model substitution, Ising model slight variation. Okay, so I will not talk much. This is how Kaufman was trying. He was trying this 3 diagram. Maybe I had to experiment and try to draw. It may end badly, but this look like pen. No, maybe this look like pen. Oh, now I cannot switch. Okay, no. Okay, I already did something wrong. Where is the pen here? No, I don't like to sign myself. Okay, I lost ability to annotate. Oh, maybe that's it. Very good, annotate. Okay, so in John's polynomial, so what Kaufman was trying to do? He was considering, he said first of all, that we don't need orientation. When in Poland with Paweł Traczyk we're discovering generalized John's polynomial, we're thinking, what happened when we have, so this diagram is okay if orientation is horizontal, but we can add other diagrams. And in fact, one of our friends, Zbyszek Nowinski, was asking us, what happened when we add this picture? I would say, told him, it has no orientation, you can't do anything. No, you can do very great things, and this is what Lou Kaufman showed. So you relate this picture, this L plus equal, and he said naively, just do it generally, that this will be A times first, B times second, and for trivial component, we put just mu, so some power. He put mu -1 because he wanted for trivial not to be 1, not mu. But that's just taste. Okay, so let's go further. Or if I go further with this, I will have my nice diagram always. So we have to go out of this, maybe erase. Yes, it works. Okay, now I hope it allowed me to go, if I cancel this, to allow me to go further. Yes, so here is just page, how to go with Lou Kaufman show, how to go from his Kaufman bracket of unoriented diagrams into John's polynomial. You have to normalize, balance this by something called right number. So if you orient, you can sum all crossings with sign. So this is a nice thing. And then Lou Kaufman and Menasco and Tistelwaite and it was Murasugi important, they solve very old conjecture called Tate conjecture using Jones polynomial and sometimes additional tools. Essentially, they put conjecture is amazing. They said if diagram is first conjecture, if diagram is alternating over, under, and there has no obviously reducible crossing, no nugatory crossing, then you cannot find different diagram with smaller number of crossings. This is amazing for not Tory. And I think not officially, but unofficially, it was one of the reasons that Jones got Fields Medal, because his theory has beautiful applications. Okay, so now let's make a list of pioneers of not theory. I always was trying to complete this, and even you see I found person before Leibniz. Probably some of you know everything about person I will pronounce in Polish Lul, but I was told that should be Dewey. So this Dewey, and is interesting because he is the first Catalonian. In Barcelona has monuments. And in the island, because I think he was built on one of the Spanish islands, he is the main historical person there. And he was universal. He was developing very nice mathematics. Now people know that he was kind of predecessor of Leibniz. But on the other hand, he was trying to convert Muslim people, but in peaceful way. He went to Africa and he was giving speeches on the streets. One successfully, second time less lucky because he was finally beaten. So anyway, very colorful person, and in history of mathematics, very, very important. But of course, then Leibniz. I should say something about Kuhn with Polish audience. Not everybody can guess that he was maybe not Polish, but he was from Gdańsk. He was Gdańsk citizen. In fact, he was born in Königsberg. Now, I don't know. Anyway, in Polish Królewiec. So this is the reason that problem of bridges of Königsberg started. Kuhn was born and educated in Königsberg, and he brought this puzzle to Gdańsk. And I cannot not say the story because this is the beginning of everything. He suggested Kuhn, not Euler. Kuhn suggested the first convincing example of this geometria situs of Euler. He suggested puzzle of bridges of Königsberg. We should add that it was Euler who solved this problem. But what was the story? Kuhn got a job in Gdańsk, and it was just before the king of Poland died. And then there was war, unfortunately, of succession between Leszczyński and Second Sas. And Gdańsk took side of Leszczyński, who was supported by France. But Sas was supported by Russia, which was much stronger. So there was siege of Gdańsk, and Gdańsk, after bombardment, have to capitulate. In fact, after half a year, have to capitulate. And it was forced to pay very big reparation. So the reparations were very big, and Gdańsk decided to ask for relief. So they chose delegation of distinguished Gdańsk citizens to be sent to Petersburg to ask Tsaritsa, to ask whoever, Anna, I think she was, for smaller reparation. And they chose distinguished citizens. But one of them was young, I didn't list him here, but young person called Echler. And he was really a scientist. Rich scientist, and he even corresponded with Leibniz, but it was he who brought Kuhn from Königsberg to Gdańsk. And really it was through this Echler when Kuhn started to communicate with Euler. In fact, story is that Echler, it's not well-known story, that Echler went to Königsberg and he was participating in meeting of New Petersburg Mathematical Society with Euler. And then at one of this meetings, he told Euler about problem of bridges of Königsberg. Because all correspondence which survive later between Kuhn and Euler is on behalf of this, between Echler and Euler on behalf of Kuhn, is referring to their previous talks. Not strictly, so there's conjecture, but very likely. Anyway, this is the beginning, even as we know, Leibniz, etc., of applied category theory. Okay, so you recognize all these names. if I spend on each of them that much time. Of course, on Gauss, I can spend even more. Everybody can on listing. Kirchhoff, I said that really there was disconnect between graph theory and knot theory later, because 1947, I didn't write here date, is the year where Kirchhoff has this famous paper about electrical networks. It is exactly the same year as Listing, student of Gauss, wrote the first booklet about knots. So, but there was not much communication. Even the Scottish group, Kelvin, Maxwell, and Tate, even if Tate was writing paper about knot theory and he did some relations, he didn't kind of do enough. And then this relation was forgotten. Maxwell is very important. Maxwell knew everything. It is Maxwell who told Tate about knots and about Listing and Gauss work on knot theory, etc. But he never published anything. So Simone, of course, Poincaré, we know little. I wrote a very long paper about little. It is not yet published, so I should not talk now because it will be till the end of my talk. Okay, and now second page. Wirtingen, Higard, then all important people. Alexander was mentioned, Alexander Polynomial. Hassemann, who knows? The first woman with essential paper on knot theory in 1916-17. Rademeister, people usually know, Foster not, and I would never learn about him, except that he lived to be 100 years old, but he's pretty important. Terasaka was the first knot theorist in Japan, and they had very nice school with finally Murasugi, and now really good. And now you see Seifert, famous topologist, and in 1930s, but now you see some people have dates. These are times when I met them, or almost met them. So with Seifert, it was like this. In 82, martial law in Poland. I was so happy they let me in September to go to Oberwolfach in Germany. But I wanted to visit my friend in Heidelberg, but I lost all addresses. I came to Heidelberg. Of course, from Poland, I didn't have any money. So I didn't know what to do. It was Sunday. So I walked to university. They didn't let me in, but they suggest just call mathematicians. So I found in telephone book they gave me Seifert and Puppe, another well-known mathematician, but not that as Seifert. So for a while, I was hesitating. Should I call Seifert first? But I decided to call Puppe first. And Puppe was very nice. He sent some student to take me, etc., etc. So I almost met Seifert then. Fox, I couldn't met. He died in 73, rather early. He was this main American knot theorist who taught about fundamental group being everything and algebraic topology. Thurston I met several times, but in particular important is he came to Warsaw for Congress of Mathematicians. It was 1 year delay because of martial law. And here the comment should be made for sure. I was talking to Thurston and he gave very nice interview, which I was circulating when Zbyszek Oziewicz, I think then was in prison. Maybe Jurek should tell me. Was he still hiding then or already in prison? Probably Jurek have no voice. Maybe he was still in hiding.
He was in 1984, Józek.
So he was still hiding.
He was, yes.
Yeah. He was not in the prison, yeah.
Yeah. So he was hiding successfully. In fact, there was one hiding person, Janek Narożniak, mathematician, who secretly attended this Congress of Mathematicians. But this was too much risking. He was not that serious as Zbyszek and his group of fighting Solidarity, Solidarność Walcząca. So probably he couldn't risk to show up at Congress, or nobody hiding could. Anyway, Conways I met a few times, but mostly I remember at meeting of IMS in 99. So there's the famous John Horton Conway, who died as well from COVID. Then Vaughan Jones, which is mentioned every time. And unfortunately, he died not from COVID, but in 2020. I knew him very well. I spent 1 year in Berkeley. He invited me. But he died with something unfortunately related with COVID, that he has some infection of air. He thought nothing serious, so he didn't look for help. Because of COVID, you don't go to hospital. And suddenly he died. It took him very quickly and he died in September of last year. Okay, so let's go. Finally, I said that next 130 pages are about scale modules, which I thought about applied category theory in this context. So, of course, first advertisement. With my students, Ria Palak-Bakshi, Diony Ibarra, Gabriel Montoya-Vega, and Deborah Weeks, we wrote the book. And our proposal was modest. We said 170 pages. And one final, as you see, after 1 year or more than 1 year, we finally deliver our draft. It has 400 pages, but it's still with referee. So I'm be glad to send chapter. I cannot send whole book. In fact, mostly because it's too big. I don't know how to send such a big file, but chapter, yes. So few chapters of them written by Ria. She just finished. She's now in Switzerland. So a few chapters were written by Ria, and she prepared transparency for her talk and then for my talk. So very nicely, I will use part of them. I still have a lot of time. I think at least 14 minutes or maybe 24 minutes. Okay, so now it is this talk. This is really based on the book. So very slow, once more. But now it will be very slow. What is skein module? Okay, it's based partial Alexander polynomial. I mentioned this already. It's based on normalization of Alexander polynomial given by Conway much later. In fact, this relation, this linear relation with pictures was already given by Alexander, but it was not normalized, so it was difficult to use. Okay, then John's polynomial, again, skein relation. Then our home-flipped polynomial, another skein relation, in fact, the same pictures, but as John's, but general variables. Then Kaufman polynomial, but it's not Kaufman bracket polynomial. It's Kaufman polynomial of two variables. It takes into account 4 pictures. Maybe I should practice maybe I shouldn't, but I would like to practice my skills. So to practice my skills, I should annotate, I should draw, I should choose probably, but all of credit is probably chosen. So now in Kaufman polynomial, we have 4 pictures, but 4 simplest symbols. Okay, so you connect them by linear relation, and you can attach to diagrams some invariant. But then knots are topological objects, so we can change diagrams, what we call by Rademeister move, by deformation in space. And then you cannot have arbitrary coefficient here, here, and here. What Kaufman found is that some coefficients should be chosen. In fact, arbitrary coefficient here, and then what he noticed, he was not using this language, but more or less that we should not use first Rademeister move. That this is not the same, as this. Why? Because it's convenient and necessary to consider frame links. What it means? That you have framing. I will have nice picture later, but you have framing. And then, of course, when you make it straight, it is not really straight, but it has kind of thing like this. I don't draw nicely, but it is twisted. So this is Kaufman polynomial. Among the singular polynomials without anything, this is the simplest. The simplest, most general. It is independent on home-flipped polynomial, but it generalized Jones. Okay, so this is my training with this. Now I should cancel this. I think if I don't erase picture, it will be on every picture later, which is not bad, but I don't like this. Oh, too late, because I have to go back to annotate, because otherwise I cannot erase. Okay. Probably there was comment to erase everything.
You can erase comments.
Erase comment, where it is. Or in erase, there's comment with everything. I don't see, so I have very few. Oh, now I have very few, so I will erase. Okay. So, and more. So this is the easy motivation coming from polynomials, from full-scale modules. So I added Kaufman bracket. In fact, Kaufman, he's here, but maybe he will talk more after. So Kaufman polynomial was created, Kaufman bracket polynomial was discovered by Kaufman few weeks after Kaufman polynomial, kind of reverse order. Okay, so what more? Then Kaufman found different version of this polynomial, Dubrovnik polynomial. In classical case, you can easily transform one to another. if you go generalize to any three-manifold, they diverge, which is interesting. Then Vasilyev-Gufarev invariant was something very fashionable, now a little out of fashion. This is kind of that we add singular knots and resolve crossing. And finally, general invariance of link in S3, which is using scale relation, whatever it means. It's a relation, usually linear relation connecting pictures. But there's no need to have linear, but it's simple. Okay, so as I was saying already, scale modules are all really generalization of these various polynomials of links from S3 to three-manifold. I should say that really theory in four-dimensional manifold is not developed, but is very interesting. So we should not limit ourselves to three-manifold. It can be any n-manifold, but four-manifold is now frontier. So anyway, there are three-manifold invariant by definition. So I introduced them, I think, in April of '87. So students, of course, stressed that I was before to live, but he probably discovered this independently. And there's plenty and plenty of them. So why are scale module important? Jokingly, I say because now Witten is interested in them. But for pure mathematicians, they have very nice structure and unknown, and it is just the beginning of study of them. Okay, so they are related with everything. Algebraic geometry, I will mention later, hyperbolic geometry, of course, Witten-Reschek into life invariant, so maybe I should rather say that there are special cases of topological quantum field theories, but maybe it will be next, exactly, topological quantum field theories. Then homological invariants, whatever it means, but probably it meant here Hovanov homology. Representation theory, especially SL2C representations, through algebraic geometry. Cluster algebras, we are supposed to learn about them because it's a new thing in knot theory. Temporal leap algebra I mentioned, and here I should tell a story. So who discovered temporal leap algebra? Of course, we think temporal leap. Maybe yes, maybe not. For sure, it was Jones who discovered them in '85. But he didn't know that there should be called temporal leap algebras. John discovered them as some von Neumann algebras, some projectors. And they were satisfying some relations, so he said it's nice to do it abstractly, like, as again, Osiewicz would love, not some things, object we don't know, but clearly defined algebras. But then somebody told Jones, I think he told even, I forgot the name. In fact, I should say more. I was corresponding about temporal leap algebra with Jones a few months before he died. And then he described me the story, which some people knew already. Evans, it was Evans in England who told me, you know, John Vaughan, that there are already theoretical physicists were considering something like this. And in fact, it is already in the book of Baxter. Book of Baxter has really clearly described axioms of temporal algebra. This is mostly about what we now call Young-Baxter equation, but temporal algebras are there. And it was before, of course, Jones. And in temporal leap paper, which is fundamental paper, but is not clearly written, it was Baxter to really referring to temporal leap defined algebra. Jones was independent. Okay. Hopf algebra, obviously very interesting. Now, Hopf algebra are competing with Frobenius algebra, which are better for knot theory. Hecke algebra, of course, no Frobenius yet. Okay. So the outline of something which I hope you don't have to see fully, but at least my student is very systematic. So what will be in the chapters? So first we give some examples, initially based on some simple thing, even simpler than Kaufman bracket, on what I call homologous scale module, homotopy scale module. They are simpler. It is possible sometimes even to compute them for every three-manifold, but they are much less powerful, smaller structure. And so second is based on Kaufman bracket. This we know a lot. Maybe this I will mention a little. So it has plenty of properties, nice torsion. It is computed for many manifolds, but not that many length spaces, some Seifert, not all even some Seifert manifolds. Poincare homologous sphere, but only torsion-free part. Then there is very important witness-finitas conjecture, which verbally I described for the Kaufman bracket scale model over field of rational function. It is always, for closed manifold, is always finitely generated. Then, in many cases, you can put algebra structure of Kaufman bracket scale model related to quantization. There's Poisson bracket, but there is nothing special there from our point of view. For people who discover from other point of view what was big discovery, but for us, it's nothing special. It's mostly take surface cross interval, take surface, and multiplication is just putting one link above another. What is bracket? Of course, the different AB minus BA in this sense, and is giving some famous Goldman bracket. Anyway, this is very interesting story, and Turayev wrote a very nice paper about this. And then there's this there's not Z, but positivity conjecture. So because probably I will not read this. We are in the case of surface cross interval. And now we have multiplication. And in my early paper, I defined what is the basis. For surface cross interval, Kaufman bracket scale model is free. So we can ask whether multiplication constants are always positive for some basis. And this is the conjecture which is partially proven. Of course, you have to change bases. These are not diagram, but everybody here knows there should be Chebyshev polynomials related with them. But positivity conjecture is partially proven. And then at the end, you have some other property of skein algebra. And finally, very nice relation to SL2C character variety, which was first discovered by Doug Bullock. But we joined this with my student Adam Sikora very early. And this is a very beautiful thing, that this Kaufman bracket scale relation really corresponds to what we call deformation or Q analog of just simple trace formula for 2x2 matrices. Very closely. But this was a big discovery. Okay, notation. I think we don't need much notation. I will explain first few pages because I don't like to talk too much. So this is the simplest scale model. One of the simplest, but I like this a lot. This is what I spent some time solving kind of exercise at the very beginning of scale models. I said, assume we have only two pictures. And the relation is just that you can change crossing. Also, it's not the simplest. This is clearly when you can change crossing, it's related to fundamental group. Let me go further. I like homology scale model. Here you just framing this one, really I like. No, this is still homotopy, but deformed. I don't like, so I found a lot of thing. Frame scale model have here a very prominent thing because we solve one problem with students. So of course, students were very proud. I will just go to one beautiful picture. Everybody knows this picture. How to change framing in three-dimensional manifold. We need non-separating S2, and we local picture around the sphere, and then we can change framing by just ambient isotopy. In fact, I draw this picture, it is almost by Rademeister. And you change framing, which is very important for scale model because scale model depend on framing, and you can change this when you have non-separating S2. But even better, you can change framing when you have two pieces, but only if they are positioned like this. So you see, when I was doing picture, I was trying to do total symmetry, not very successful, but almost. And if you can see me, this, every person who knows can do this. I will not do this, of course. You take two cups, one in left hand, one in right hand, and then you do something. I don't like to spill coffee on my computer, so I will not finish, but something like this. And you will see that you make double twist. Belt trick, but here is double belt trick. Well, it's the same trick, of course. Dirac trick, yeah? Here should be written Dirac. I'm not sure whether Dirac was thinking what happened when you have two particles. But anyway, okay. So we prove something using this Dirac trick. The only possible of putting torsion when you have only framing is by Dirac trick. But really the scale model, which I really like, it was the very beginning, is this, that we think that we can smooth crossing. I put Q here, and then I was able totally to compute scale model when only we relate these two things in general tree manifold. If Q is equal 1, it looks a little like homology, because in homology you can make these two pictures in homology represent the same element. But in homology, but when you put Q, you have some deformed homology. So I think I like this picture so much that I will end with this. This is not true. I proved this much before, but it was published then. Okay. And the third scale model is something with Kaufman. This is with home flipped. So of course, initially I was very much interested. This was for me motivated for scale models, but I don't like to go. I have only more 130, whatever, 133 pictures, and all of them look similar. So this is applied category theory. So you can play this, almost everything is open. With Kaufman bracket, we know something. With Humphreys, not much. For length spaces, even is not totally computed. Third scale model, it is computed for LP1 length space, so it shows that nothing almost is known. In fact, I would prefer to have last 5 or 9 minutes for question, or maybe question related to Zbyszek. I didn't describe how I met him. Now, of course, maybe my memory is not working very well, but thank you. Jurek has voice.
Yeah, thank you very much, Joseph. And yeah, indeed, we have about 8 minutes for talks, because remember, you have to have a minute to uptake your duties as a session chairman.
Exactly.
So anybody with a question? There's 14 new messages. Let's see whether some are questions.
Yeah.
It may be about, oh yeah, Lou, very good.
Question?
Okay, go ahead.
Well, could you say a little more about how you see Raman Lull as an op theorist?
I used to have one of the picture of his not theorist really, as apply category theory person, because it's about Zbyszek. But of course, this apply category theory is language for us. And probably you can say much more because you discovered Kaufman bracket, where you know, probably were very well knowledgeable about category theory. Because
So you're thinking of Raman Lull as a predecessor of category theory.
Of Leibniz, yeah, of category
and
theory.
Category theory is certainly can be thought of as a, you can think of knot theory as a kind of category theory. So yeah.
Kind of, but this is nice thing. I'm not. I think later Zbyszek was talking about this, because this is category. This kind of manipulation of symbols, but embedding is important. This you know very well. But I think we should think like this: we manipulate symbol, but symbol after rotation is different symbol. And
right.
And
so it's the placement problem of symbols.
Exactly. And we should think like about this. And so this question to you, Lou, what is really the best category of knots? Because standardly we see it as cobordism, and probably it is pretty good. But I'm not that happy. I would say like Leibniz. This is good. I'm not happy with this.
But you can think of the knot diagrams themselves as symbols in relation to one another, where the symbols are arrows, the arrows in the knot diagram, and the arrows point from arrows to arrows. So it's an infinity category. A knot diagram is an infinity category.
Okay.
A reflexive category where all morphisms are morphisms between morphisms.
So once more, what are morphisms? I need it more naively. You say objects are arrows.
Take a knot diagram. The objects are the arrows and the morphisms are the arrows in the knot diagram. An arrow in a knot diagram begins on an arrow and it ends on another arrow.
Yes.
So it's a category. It generates a category where the objects and the morphisms are identical. Not quite identical. There are more morphisms than there are objects. But every object is a morphism.
Okay.
So and this is like a Lullian, knot diagram is like a Lullian machine.
You rotate pieces and then have, this real machine is really category, because objects are, of course, the circles and morphism are rotations, maybe.
Yeah.
I had nice pictures of this Lullian, Julian, whatever machines, but not here. Okay, very good. So anyway, rather the point is what you gave another example, that there's not clear what should be category of knots. Is a solution, but classical is cobordism, but there are other possibilities.
Right.
All right, thank you. Some other questions, perhaps, or remarks? Lul was also, or Joy, you said this is
Joy, Lul, yeah, Joy.
It was enthusiasm of this Theatrum Mundi, the idea that you can take the basic ideas of philosophy and put them into this like big theater and see the connections between them. That's the beginning of the applied graph theory, right? So it's kind of close.
Yeah.
He definitely should be put at the beginning of the story.
This for sure, because some of his pictures are just complete graphs, so I don't know, 10 vertices or something like this, but showing connections, yeah. Or he has this science tree or whatever tree, they are clearly trees.
Yeah.
But that's up to interpretation.
Oh, another interesting historical bit is that Temperley actually discovered the braid group representation associated with the Temperley-Leib algebra.
Okay.
But he didn't go farther. He didn't try. He didn't try to make a knot invariant.
Notice relation. So Jones was not totally wrong, because he sees some relation related to braid, but already Temperley as well see that his algebra is related to braids. I should write comment because I wrote something about this story. But is it in his fundamental paper or is something else? Is Temperley paper or is different?
I'm going to have to look up where Temperley did that for you, for myself as well, but I know it's true.
Yeah, because there's many papers by him, but famous for us is this Temperley, of course.
Józek, I have a question here.
Develop geometric interpretation, Lou, for you. When you develop geometric interpretation of Temperley algebra, was it knowing, of course, knowing Jones, yeah, but knowing...
You mean the diagrammatic?
Yeah, diagrammatic.
I think the diagrammatic interpretation is due to myself.
Yeah, it's yours, but did you know about Jones' work or maybe Baxter's book?
No, it's not there.
So this is just from scratch, playing with pictures,
that connection interpretation is due to me, as far as I know. But of course, it has its roots, although I didn't know about it at the time, in Brouwer algebra and things like that.
But Brouwer is for all connections, not crossing.
That's right. That's right.
But Brouwer, of course, was before. Brouwer was before Temperley, much more before the war, 39 or something.
Józek, there is a question for you. There is a question for you from Michael Heather, I understand. He asks, what is the point of knot theory if it cannot actually represent the tensile nature of real physical knots? It's a philosophical question.
For whom is question? Maybe for Lou better.
Well, I gave an answer in the chat line. I'll say it again. We start with topological models, but then we add extra structure and do think about physical knotting. And lots of people do a lot of work on physical knotting and computer modeling of it. It's actually a big part of knot theory. So it isn't true that knot theory is just about pure topological relations. But the other side of it is that it's very remarkable that the purely topological part of knot theory is deeply related to physics, to statistical mechanics and to quantum field theory and to the basics of quantum gravity, as people are trying to do it through loop quantum gravity and other things. So there's something about topology that we haven't understood yet in relation to physics.
Yeah.
All right. Thank you. Józek, you have just 1 minute to resume your duties.
Okay, so I'm resting for 1 minute and then I will start. Okay. And according to my schedule, the next talk is by Giovanni Gregori. Are you there? Or maybe I'm mixing everything and I have all.
Yes, you're hearing me?
Very good. So you are there. We start in 1 minute.
Thank you.
So maybe you should try to share screen, but we have 1 minute to relax. I will try this trick, but only with one. Okay, we have your screen, maybe.
Wow.
Okay, I'm ready.
Okay, so we can start. And it is a pleasure to start this afternoon session devoted to memory of Professor Zbigniew Oziewicz. And the talk is by Giovanni Gregori, and he talks about gold as we see it, golden ratio and variational principles, cyclic and wave phenomena and quanta. Welcome.
Thank you. Good afternoon or good night. And I thank you for inviting me. With great emotion and sorrow, I feel honored to contribute a little bit to celebrate the big new. I report on some ideas that were developed in a group of friends in an informal way from all over the world, and the BU contributed to this, to the development of these ideas. And then we decided to prepare something to honor his memory. And I'll talk about two items. One is on the golden ratio and its physical meaning, and on the cyclic phenomena, and including the structure of the photon. I will start now from the very elementary definition of the Fibonacci numbers. It's the classical argument by Fibonacci of the pairs of rabbits. And there are several other definitions, obviously. You get the series of Fibonacci numbers, and the ratios of successive numbers are converged towards the finite, the golden ratio phi, which is an irrational number. And another item is the golden ratio conjugate. These are very classical and I would say elementary information. The symbol is classic, is derived from the Doric architect Thales, and Parthenon pyramids and the Cathedral of Notre Dame, etc. But an incredible amount of case histories are observed in physics, in chemistry, in biology, in psychology, in arts, in music, etc. And one wonders, what does this mean? We propose a speculation much behind any formal mathematics that, as I repeat, was born by a joint discussion after several friends. A key concept that I will stress is the quasi-equilibrium. That is, we observe a natural system while we progress towards a final equilibrium, but through a sequence of states of quasi-equilibrium. And this is the golden, every Fibonacci number or every rounded off value of this irrational number can be supposed to be representative of a state of the evolution of the system towards equilibrium. And that is, every state ought to be related in some way to Fibonacci numbers, being a quasi-equilibrium state. Hence, if phi would not be irrational, we could not even define or detect time, as the world would be just a dead swan, and with no evolution, we could not detect the evolution, the flow of time. Now, let me introduce a few definitions that can be called presumptuously golden rule axioms. They are some kind of a working framework, and I'll insist on two aspects, on the additivity and on the variational constraint. What do I mean by additivity? Additivity is if you have two natural systems that satisfy the same laws, the sum of the two systems, whenever it can be defined, satisfy the same law. That is, two couple of rabbits satisfy the same law of one rabbit. And in general, the relationships that are satisfied by every natural system may be even unknown, but this relationship must exist. This is assumptions. Then, suppose that A and B satisfy the aforementioned properties. Additivity means that the characteristics of either A or B or A plus B, whenever can be defined, are such that their evolution shares identical natural analogous features. Now, there is another key point, is that we assume that it is possible to associate to the system A, capital A scalar parameter A, and to a system capital B, a scalar parameter B, and that to A plus B, it is possible to assign the sum A plus B. This is part of the language. This is part of the assumption that we arbitrary choice, and we assume that the evolution of A and B is characterized by the ratio A over B, and that similarly the evolution of the composite system A plus B is characterized by the ratio A plus B over A. Now, this is the physical, the geometrical interpretation of, this. We are going to assume that these two ratios are equal. And so that is, if I say that A, the ratio of A over B is equal to the ratio of A plus B over A, this is the geometrical interpretation recently published. This is the definition of self-similarity, which is exactly the property that is shared by fractals. Therefore, if you, it is found that when additivity and the variation principle, I will show this, when additivity and variation principle are satisfied by the system satisfies the golden ratio rule. Or self-similarity and variation principle are sufficient for the golden ratio, the golden rule. But now the point is that since the golden ratio is a very frequent occurrence, several natural systems may share a golden rule, and this means that this logical scheme can work even when we are eventually incapable of assessing the definition of A, B, and A plus B. Now, let me come back to the fact that we assumed that the A and B are scalar. That means that the behavior of a couple of rabbits is related to the behavior of all other rabbits in the world. Now, consider the simplest case of A, B, and A plus B as scalar and one-dimensional scalar. Then, if you put that A plus B over A is equal to OAB, you just solve this and you just find that this is simple algebra. You find the golden ratio. Second solution is the golden ratio conjugate of the golden ratio. This is just formal algebra that is just related to this very, very simple assumption that, however, is found in a wide variety of phenomena. Now, it is possible to think about a generalization of this concept of A and B scalar. However, there is a point is that the action-reaction principle enters into play, as if A over B is somewhat related to the influence of A on B, and B over A is related to the influence of B on A. And you just find that phi is equal to 1 over capital phi. That is, the action-reaction principle is related to the fact that you use a ratio here. You cannot use another function. In the case that instead of a scalar A or B, one is using some multidimensional index associated to A and B, that some other variation principle is chosen, then the ratio of the invariant A over B, one must always choose a function that satisfies the action-reaction principle. Now, therefore, a related argument is with the reasonable extension. Another concept is the minimum size system. That is, a natural system is it can be composite of several natural systems. It's the sum like A plus B and so on. But therefore, a composite system can eventually be divided into other subsystems. But a subsystem cannot be eventually divided. Evidently, in the rabbit problem, the minimal system is the male and the female, the birth and the dog. That is, it may not be possible to define the natural system to our knowledge, but it is important that the minimal system exists, as this has important implications. The focus is specific observational, I mean, not only physical systems, they're physical, chemical, biological, psychological, artistic. Therefore, we called theorem of golden additivity. If a natural system satisfies additivity, two systems A and two systems A
Somehow we lost the voice. Is it everybody, or I lost voice?
I think Giovanni's microphone seems to be crossed. So, Giovanni, you have to unmute yourself.
Yeah, unmute.
Maybe disconnected himself. He unmuted.
Okay, now it's okay?
Yes.
Yes.
Okay.
Yes, now we can hear you.
Okay. Then. Okay. Okay, if a natural system satisfies additivity and if any two systems may possess respective scalar quantity A and B such that the system has invariant B over A, all systems satisfy the golden rule. The ultimate asymptotic equilibrium is attained whenever A over B is equal to phi. This is a surprising result, and the irrationality of phi is crucial, as where the phi is rational, we would detect no flow of time, no friction, no evolution of anything. We would not, that is, time is observed precisely because phi is irrational. If where phi is rational, the world would be timeless. The sheer quantity of a natural system that displays a golden ratio and fractality implies that several phenomena exist that either permit the definition of some eventually unknown, though existing, scalar parameter A, B, and A plus B, or rely on some equivalent, more intricate parameters. In fact, if some phenomenon does not satisfy such a property, this phenomenon would be out of time. It is difficult to imagine how a phenomenon could not respect the mysterious golden ratio. Therefore, the crucial relation is the association between phi and the prime numbers. That is, we mentioned that phi ought to be associated with the numbers of the Fibonacci sequence or other. And the point is that we should distinguish different subsets of Fibonacci numbers such that they can be associated to the minimal system, and they called prime natural system or prime systems. And this is possible through the astute suggestion by Christopher Monckton of Branchley, who is one of the co-authors of this talk, who pointed out that the golden ratio is intimately connected with the demonstration of the Goldbach conjecture. Why minimal systems are important? Consider, for instance, some kind of trees. They are similar to each other, but they have leaves of different forms, different shapes. Evidently, they rely on a set of basic primary minimal system. This obviously is speculative. Now, the binary or strong Goldbach conjecture is that for every even number, every even number is the result of a sum of two prime numbers. The conjecture is not proven, but it is checked for all figures, for all numbers, for all non-numbers. Monckton defines a large set of pairs that satisfy the golden conjecture. He selects the subsets. The criterion is rather lengthy, and you will see it on the paper. But he separates the number of elements of the selected set from the number of elements of a selected set. Finally, he considers random n between 1,000 and 10 million, and he suggests the Monckton conjecture that the ratio of the number of selected to unselected sets is asymptotic to the golden ratio conjugate. Therefore, the concern is therefore about envisaging the relation between the Monckton selected Goldbach pairs, the prime systems, and observations. This is part of the language, and Monckton selection is based on divisibility, and divisibility implies the number cannot be associated to prime numbers. Details in the paper. And according to the Goldbach-Monckton conjecture, the logical step is to envisage that every natural state associated with one Fibonacci number ought to be associated with a subset of prime system, every one associated with some prime Fibonacci number. Therefore, one matters what is the connection between prime numbers and the golden ratio. This is the point that should be observed. Summarizing, not all primes are Fibonacci numbers. Therefore, the Fibonacci sequence is not an exhaustive symbolic representation of all possible physical states of the system. Every Fibonacci number is a representative quasi-equilibrium state. Fibonacci sequence describes the evolution of the system according to this Goldbach-Monckton conjecture. Every system max and minimal states. Can this serve? This is the end of the first topic. Oh no, not all, not yet. Living beings want security. Then they search for security as a survival instinct. Living beings recognize the golden ratio. That is, it is something that is predictable. They feel sure, they feel security. Human psychology calls beauty the same feeling of regularities of security that non-humans call survival instinct. In music, this can be measured quantitatively as the musical chords and sounds that are permitted by the theory of harmony is based on the golden ratio. That is, it is unbelievable that the human brain is in effect a power analog computer, as human brains immediately recognize from the perception, sensorial perception of sound, or from by looking at the picture, at the picture by Leonardo or by Raphael or so, you immediately perceive what is beautiful and what is not beautiful. The human brain is a powerful computer that in real time almost immediately perceives whether a sound is harmony or not. If one able to translate some difficult problem into sounds, in principle, one might solve extremely intricate computation by exploiting such a natural analog computer. Now let me shift at the second part that was built with several contacts I had personally with the big new. The D'Alembert equation. D'Alembert solved the equation for the vibration of the violin string and interpreted the two solutions like waves propagating along the string in opposite directions. Maxwell did something equivalent with electromagnetic waves and interpreted like waves propagating in opposite direction. This is what I'm just saying, that the electromagnetic waves, the two solutions are associated to electromagnetic waves with defined by mini photons of opposite polarity. I'm explaining what I mean. The Schrödinger equation applies to a photon. Photon is considered like a finite volley of mini photons, and the volley of monophotons of both opposite polarity gives rise to the two solutions that are the mirror of matter and antimatter of the alpha world and gamma world, as I'm going to explain. Let me just introduce this concept. A photon can be conceived like an entire whole volley of mini photons. It is released altogether a very complicated engine that is represented by the atom or an ion that emits this photon. But now consider the same photon as a volley of single mini photons. And if you have the light source move towards the receiver, or it moves away from the receiver, you have the wavelength is changed, the distance is changed, and this is the Doppler effect explained in terms of mini photons. Now, consider a polarized wave, and consider a wave composed of elements Ke and Kh that Kh and Kh, and that have opposite different polarity. Note that the second polarity, the second line is the normal, the standard polarity, the standard polarity, and the standard parity, and the second line is the reverse, is the opposite parity, and this is equivalent to a Faraday law where the induction currents has opposite direction. This is what occurs in the anti-world of antimatter. The concept of multiple photons was introduced as part of the more general treatment. The standard concept of photon must be related to the wave train of beam of light. A photon is considered a finite volley of mini photons. And note that this argument requires that we can refer to an absolute frame of reference. Indeed, Einstein never denied this possibility, even though he tried to represent, to describe to physics and with no need to refer to an absolute reference. I had a long and very fruitful discussion on these points with Vignew, and I am feel very grateful to him. Now, let me remind about a comment by Finzi. Finzi was a teacher, a well-known professor at the Polytechnical School in Milan. Every cyclic phenomenon requires the occurrence of a non-vanishing delay encompassing one full wavelength. And if you use a simple logical abstraction, that is, this is just mathematics, you assume that there is a D'Alembert equation that is related to something that has a cyclic phenomenon like a wave, and you find that just because there is a wavelength to be respected, that there is some number that is n, that is integer. That is, you find that in either one information relation, it is concluded that the light wave must comprise discrete corpuscles. One light wave cannot be continuous and infinitesimal. Accordingly, a photon too must comprise distinct components whenever the formation delay of one wavelength is taken into account. This is not likely to be a mere coincidence. This is consistent with the possibility of continuity of infinitesimal quantity in natural phenomena. The Schrödinger equation is a complex function equivalent of the D'Alembert equation. The two solutions represent the Schrödinger equation represent non-absolute complex conjugate worlds. Alpha, that is the world of matter, and gamma world, that is the world of antimatter. And they both originated from the absolute and timeless beta world. That is, much like a photon eventually materialized into a couple of a positron, electron, and positron that later on annihilates and becomes a photon. You have the beta, the timeless absolute beta world eventually materializes into alpha and gamma world, into space and anti-space, into matter and antimatter, and that eventually returns back into the timeless beta world. That is, you have the absolute timeless beta world eventually materialized into the complex conjugate beta worlds that are not absolute, that are transient and provisional symmetric features before collapsing and deteriorating into absolute timeless world. That in the note that there is the two worlds are complex conjugate of one another. That is, natural reality is not associated to integer numbers and to real numbers. It is intrinsically associated to the complex conjugate functions, so that you have a world where you have the time error is in one direction, and the world where the time error is the opposite direction. Energy is a positive and negative, mass is positive and negative, and in this way also the paradox of the growing enthalpy is solved. The golden, in any event, no such easy one scalar quantity A, B can be associated to the Schrödinger equation. Maybe one could, this is just a guess, one could associate the spectrum, the entire spectrum of an element to a given state A. That is, just to give an example, assume that the hydrogen atom and an oxygen atom are two minimal natural systems identified with the system A, capital A, capital B, while the radical OH is the sum of AB. The question is whether a golden rule determines the spectrum of OH on the basis of the spectra of the hydrogen and oxygen. Obviously, I have no reply for this. This is just a guess related to this conclusion. The golden ratio, additivity or self-similarity, variational principle, cyclic and Will phenomena, and quanta are closely connected properties shared by natural reality well beyond the physical domain. Even psychological items such as stock exchange behavior, beauty or harmony, as well as the relation with chaos theory and the exploitation of the prodigious power of the human brain as an analog computer, are likely to be topics of future concentrated thought following for some significant achievement. A simple rationality relates additivity, fractality, and the variation principle. The immense capability of living beings to recognize golden ratio for survival, and the capability of human brain to recognize golden ratio to define beauty. Therefore, in principle, this capability of human brain ought to be exploited like an unprecedented and very powerful analog computer. That is the question, why the golden ratio is so often found in nature. It is no more, so much, it does not look very such a mysterious feature of natural reality. I thank you very much for your attention.
Thank you very much. And maybe just one short question, if any, because we are over time. Yeah, Lou. Mm-hmm.
This isn't exactly a question, it's a reference question. I would like to be able to see, Professor, your website and possibly also the reference to the paper by Monckton. Do you have references to those, like a website for yourself?
The paper by Ron Monckton gives the proofs in our paper that we prepared for the contribution to this meeting. It's not published, it is only a preprint. One should
but you have a paper that's available?
Well, a draft of the paper was already sent to the organization meeting, and there are the addition of the relationship with the self-similarity has been added now, and has been updated, and it would be sent me by a few days. It's already prepared, but I circulated it with the all co-authors for. But I am waiting. They are giving me the green.
Then I would appreciate your email address. Perhaps you could put it on the chat line, and then it would be possible to write to you and ask for reference.
Yes. Now I am sorry. I don't see my image as I switched off my screen, and I don't see how I could send you my. Can you
in the red line up in the screen you can put off.
I want to take off the.
If there is time.
Si quieren, que yo se lo comparto por correo electrónico al doctor Kaufman.
Sí, pero.
Oh, okay. Okay. Now
If there is time, I have a curiosity question for Giovanni.
Sure, ask, yeah.
Giovanni, are you available?
Yes. Yeah,
this is mainly a curiosity question. I'm interested in your comments. I do not know its value. The point is the following, that the abstract axiom of a numeric field do not necessarily demand that the multiplicative unit is the number 1. It can be any positive number. So you can assume, for instance, the multiplicative unit number value 3. But then you have to change the multiplication to verify the axiom. You have to insert in between any multiplication the inverse of the number that you have selected. In this case will be 1/3. And then 3 indeed is the right and left multiplicative unit. You verify all the axioms. The curiosity question is the following. that those are called incidentally isonumbers. They are used in very advanced cryptograms, used in apparently in the USA and also in England, I'm told. Now, the question that I have not seen this aspect investigated. So it appears that as a result of this property of the isonumbers, it appears that the numeric value of the Fibonacci number are not absolutely absolute, because they depend on the assumed multiplicative unit. What remains absolutely valid, of course, is the rule according to which you construct the Fibonacci number. But this is the question. Giovanni appreciates his curiosity. What is your view about this kind of change of the numeric value of the Fibonacci number, while the rules for their construction remain, of course, valid?
Now, I'm not sure I understood perfectly your question, but certainly there is nothing magic in Fibonacci's number. Fibonacci's number is maybe the best known sequence of numbers. However, there are other sequences of numbers that converge to the golden ratio. They are slightly different. One of our co-authors, Arnaldo D'Amico, who unfortunately left us a few months ago. In a few months I lost three very, very good friends of mine, and I was very sad the last months of the past year. And he had investigated with some co-workers other series of numbers. I consider in the talk in 15-20 minutes, I could not introduce this. Otherwise, we have prepared a draft that is much over 100 pages, and it is not a paper. It should be a small book. We mentioned that the Fibonacci numbers, as the Fibonacci numbers are the best known, if you like, most elementary case history. The point that we like to stress that when we began considering this problem, we were looking at the golden ratio as something which was just mysterious, we were incapable to have any idea. And now we arrived to whether the association is to the Fibonacci sequence or to any other sequence, whether you use the simple scalar quantities A, B, and A plus B, whatever the meaning of A, B, and B plus B is, you find that the additivity and variation principle just lead to the golden ratio. Variation principles were, for over 2,000 years, remained in the realm of intuition, nothing rigorous. The rigor was brought only in the 1820s, 1830s by Hamilton and Jacobi. But here in my presentation deals with ideas that are very vague, very intuitive. It is not, there is nothing formal. That is, other talks are wonderful, axiomatic, rigorous formulation in the terms of mathematics. When we have the golden ratio, you see that the leaves of a tree respect or some very elementary living forms respect the golden ratio. You are afraid. You say, how can I understand this? We think that we have started to have some kind of light at the end of the tunnel. Obviously, you can use also better numbers than the Fibonacci's. You have the association of abstract concept of prime numbers and of a special category, a subset of prime numbers with some concrete phenomenon that you touch with your hands or you measure with your instruments. This is something that is actually a challenge, but we guess that we have started to see a light at the end of the tunnel. That is my point. I don't know if I replied to your doubt. I understand very well your point. You know, that this is not a rigorous mathematical theory. This is just an intuition, an interpretation. Zbigniew was I would say a natural philosopher, like Isaac Newton told. That is, he was not a scientist that was specially concentrated on his specialty. And this is why it was possible to talk with him about a wonderful spectrum of items. And very often I could not follow him completely, as my background was not sufficient, but he was talking with me about geophysics, as well as the earth physics, with a great competence. That is why it was born, these ideas. But we have to manage the observational reality that we can understand also, we can observe without understanding. We are blind in several respects. And this is my point. I don't know if you are satisfied of my reply.
Thank you.
Thank you. Probably
Intuition.
next talk should start soon. So very interesting discussion, but probably we should start.
Well, I thank you very much.
We can correspond. Giovanni, we can correspond. Thank you for your answer. Thank you. Ladies and gentlemen, I'm going to have dinner now, so good night.
Good night.
Here it is a good night. It is almost 1 p.m., 1 a.m. here.
But still we have 3 talks, and the next one is about Juan Antonio Perez. So probably you can prepare your talk, share with us.
I need some food and then I'll be back. Thank you.
Thank you. Yeah.
Well, good afternoon, everyone.
Yes, so it's a pleasure to introduce the next speaker, Juan Antonio Perez, and he will talk about some categories of Alexandrov spaces. Welcome.
Thank you very much. I'm very pleased to be here in this very nice conference. I'm grateful to Lady Dr. Hilda Colin and Dr. Jesus Cruz because of their invitation to present this work here, this talk here. And I have to say that I'm in depth with Zbyszek, with Zbigniew Jewicz. He brought to me the idea of applied category theory. We worked together during some time in categorical calculus. And at the time, I'm working in something that I call the Ojewicz integral. Due to those very nice discussions we had with him, and also I can remember very gratefully these conversations about Morin's complex thinking, even together with Dr. Aida Colin. We talked several times about the philosophical analogy of complex thinking with category theory. And even we were together in a document. And well, I'm very pleased here. And I could talk about several things that I worked together with Dr. Ojewicz, but this time I choose for this evening to talk about Alexandrov spaces. I have to say that this idea, it was new for me when I met Dr. Ojewicz, applied category theory. Now I'm working on several things applying category theory like functional programming languages, and something about design patterns in software engineering, and of course, classification of topological spaces. And I use it as well to understand better Alexander spaces. These conversations about category theory conducted me to Allegory theory, which is a very good tool to understand Alexander spaces. Well, I start recalling the works by Michael McCord and Richard Stong in 1966 about the classification of finite topological spaces. For a long time, for a long period, it was abandoned until the very nice book by Jonathan Mabang in the 2011. The first works by McCord dealt with homology, singular homology on finite topological spaces. These were forgotten until Jonathan Barmack and Daniel Keelan in 78 and Peter May in 2012. I follow the idea of a category and allegory following Freud and Skedroff, this beautiful book called like that, Categories, Allegories, and the idea found in this beautiful book by Ojevich and Velázquez about Gráficas de Gráficas. Also, I end this talk with a very simple proof of the Kenneth impossibility, the arrow impossibility theorem about the electoral systems, which was proved by Graciela Cicilniski in 1987 with 2 papers, another one in 1980, proving a theorem that she called the resolution theorem. And using Alexander spaces, I give here a very nice and short proof of this arrows impossibility theorem. Well, I start saying that this is the contents of my talk today, category theories and allegories. Of course, I will talk about Alexander spaces, and also finally about function spaces and products. Of course, always, all the time, about Alexander spaces. I will start with the idea of how to understand category theory. A category is a collection of some entities called morphisms, and this collection comes together with 2 unary operations, domain and codomain, and a binary operation which is associative called composition, which is performed on pairs of composable morphisms. And it behaves like this. The domain at the codomain of a morphisms is also a morphism. So at the beginning, there are no objects. We can see a diagram of morphisms like this picture on the top, and the composition looks like this below this sheet. Now, domain and codomain as functions, as applications, are idempotent, and also domain is the identity on codomain, and codomain is identity on domain. They are identities on each other. With these ideas, we can prove that the image of domain and codomain coincide, and this common image is a subcollection of the collection C, and this called the collection of objects. A category C is an discrete category if and only if domain and codomain is the identity on C. That is, if all of the objects are sorry, if all isomorphism is an object. Also, we have that alpha composite with B is an object. Also, beta and alpha is an object following these ideas. Now, connectedness is a very nice property on categories, and of course, is also a very nice property on Alexander spaces. And it is defined by defining a zigzag, which is called by Barman in his beautiful book, a fence. A fence is just a collection of chains gluing together, like in this picture. Of course, some of them can be redundant, and it's I will note this like x with its ends x0 and xn, because they are the ends of the first and the last chains in this fence or this zigzag. Of course, any of these chains could be a maximal chain. Thus, a category is connected if and only if every two objects are the ends, the extremes of a fence, like in this equation in here. Thus, as an example, the category Z, the category of sets and functions, is a connected category because we can see for any two sets, A and B, this fence composed by two chains. This arrow here from the empty set to A is just the inclusion, and also in this composition, this change is the inclusion of the empty set in the set B. Oh dear. Oh, it doesn't change. Oh, sorry. Okay. Now functors just behave as we expected from them to be working. They correspond, this behavior correspond to this commutative diagram at the bottom of this picture. Now, a natural transformation then is an endofunctor on the category of functors from two given categories C and D. So, if F is an endofunctor in a category in given morphisms with domain X and codomain Y, then a functor, which is identity on objects, gives you another morphisms from X to Y. In the same way, a natural transformation goes from a category C to a category D with a functor F, and this natural transformation gives you a new functor from the very same categories in here. So this is following the ideas by Ojevich that we can find in this book by Ojevich and Velasquez about morphisms, functors, and natural transformations, thought as 0 morphisms, 1 morphisms, 2 morphisms, and 3 morphisms. Well, now an allegory is a very special kind of category which is equipped with an anti-inviolative unary operations called reciprocation. Sometimes it's called the opposite of dual. And this diagram shows the behavior of the composition respect to the reciprocation. Also, an allegory has a commutative and associative operation that we call intersection because of its analogy with the one in the category set. Okay, let me put this something here. Okay, the axioms for an allegory are the following ones. Those are very simple: idempotency, distributivity, semi-distributivity, and maybe the most difficult one, the most difficult to see at the very first sight, is modularity. Now, the inclusion, as in the category set, means that sigma is a neutral element for rho respect to the intersection. That is, that rho intersection sigma is equal to rho. Now, we go then from the category sets whose objects are sets and whose morphisms are functions to an allegory which contains the category set. This allegory is the A set whose objects are sets and whose morphisms are relations. This is a very nice and useful idea to work in with Alexander spaces. Now we found that categories thing that is the category of the thing categories. That means the preordered sets, preord, which contains the preordered sets, the graphs, which is the category of oriented graphs, and Alex, which is the category of Alexander spaces as a topological subcategory, are all of them each isomorphic to each other. And also they are isomorphic as allegories. The categories, the thing which contains the thing categories with which is a quotient category of thing, in the same way that poset, the category of all posets, partially of their sets, is a quotient category of the category preordered, which contains the preordered sets. The graph 0 with the graphs with no loops, and the Alexander spaces, which are T0, which means that all of its points are topologically distinguishable. Those four categories are also isomorphic to each other as allegories. And we find also that these four categories in the first theorem and those four categories in the second corollary, in second proposition, are pairs of equivalent allegories. All of them are allegories. Now, Alexander phases. As we know, Alexander topology on a set X is a topology closed on their intersections. So any finite space, any finite topological space is an Alexander space, trivially. A feature of these topological spaces is that every point has a minimal neighborhood, and this is defined as the intersection of all of their neighborhood system. Thus, in Alexander space, we can define a preorder, but in this way: X is less or equal than Y if and only if X belongs to the minimal neighborhood of Y, if and only if the minimal neighborhood of X is contained in the minimal neighborhood of Y. So the first thing is definition, the second two things are equivalent, obviously. Sierpinski space is a very nice Alexander space because it's the smallest one, which is very interesting because every Alexander space can be constructed with Sierpinski space as a building block. Sierpinski space may be thought as an ordinal 2, as the ordinal 2, where the underlying set is, oh, I'm sorry, I made a mistake. The Sierpinski space on the set 2, which is an ordinal and has 2 elements, has the set 1 as the only non-trivial open set. So the Sierpinski topology may be seen as the ordinal 3. So Sierpinski space may be pictured as this oriented graph here on the left, and also it has a diagram as this one on the right-hand side. An example, a very nice example, is the one of the digital line, which is very useful also for in engineering, for working with images. Also, a very good thing in Alexander spaces are minimal models with models that are finite spaces of minimal cardinality with the same homotopy type that a given space. We can see here the join of 2 zero spheres, which is the non-Hausdorff join, and this is pictured here, and this is the minimal model for the circle, for the 1 sphere. And also very typical Alexander spaces are the star topologies, which are reciprocal to each other. Connectable points are given by homotopic maps. Let's see. H in C is a preorder set X in a preorder set X is a totally ordered subset, as is written there. 2 points are connectable if and only if the constant maps is hat and y hat are homotopics. So we can say that 2 connectable points are homotopic points. Now, connectedness is a very nice property, and it is shared in the same way by topological spaces as path-connected spaces when they are Alexander spaces, as preordered sets, as categories, as the graph, and weakly connected as graphs. So we can see connectedness in Alexander space in several ways. Now, we defined a functor which is given an Alexandrov topological space. We can find an Alexandrov topological space T0 just by calculating the Kolmogorov quotient of this topological space. But if we want this topological space to be the minimum one, this is the space which is has the same homotopy type, but with the smallest cardinality, this space, which is not even proved this today, if it is unique. Uniqueness is not proved as far as I know. Diamond shape, I have to say here that diamond shaped spaces are called by my student Marlene Solis and myself. We call them in Spanish espacios farol, because of this shape corresponds to these typical paper lamps used in typical Mexican parties. Well, this picture here shows an outline of the proof of diamond shaped spaces are null-homotopic. This is the Q is a quotient and S is a section on the original space. So that means that the space on the middle is a strong information retract of the ferrule. Okay. Now we say that Alexander space T0 having a minimum or a maximum is contractible. A an example of this are the star topologies showed in this picture. Okay, and this proposition that I cannot know because of some bar here. Okay, the core x naught of an Alexander space, X is a strong deformation refract. This is proved very easily. Now, compactness on Alexander spaces seems to be a very useless property, but in fact, it is very important. An Alexander space is a compact space if and only if the minimal basis, I have to say that an Alexander space has always a unique minimal basis. So if this minimal basis contains a finite cover, then and only then, the Alexander space, the corresponding Alexander space, is a compact space. Also, thus an Alexander space admits a unique minimal open cover of minimal neighborhood because of the things I said about the uniqueness of the minimal basis. This is a very nice theorem about Alexander T0 space is compact if and only when it is T0, if and only if there is a finite set A of maximal elements. That's a very nice thing. So Boolean groups, for instance, are compact spaces, and they are the opposite of themselves. So they and the opposite are the same spaces. And these are spaces, compact spaces of index and co-index 1, because they have one minimal and one maximal element. So index is an invariant of compact topological Alexander spaces. This is another very nice example, this of divisibility, which is also a compact space with underlying set in the natural numbers, and it has also index and co-index 1, where the minimal basis is made of the sets of divisors of a given element, of a given number. This is some technical results, and they are nice, but a bit technical. So I carry on. A very nice thing about Alexandrov topological spaces is that when we take infinite products, the Alexandrov topology on this product does not coincide with the topology of the order product. This is easily seen with this example where we take the ordinal n as the set with the previous ordinals, and we take the product of all of those. And of course, this is an Alexander space, but as Alexander space, the sequence, the constant sequence of zeros is open in this topology, but of course is not open in the product topology. So in product, this on products, the order topology, the pre-order topology, the Alexander topology, and the compact the product topology does not coincide all the time. Another example is this one given by the non-Hausdorff suspension of a space. We show here the non-Hausdorff suspension of a point. We can see here the join of 2 points, which is the Sierpinski space, and this is the product of twice suspension of 1 point. And of course, an infinite product of this space, this suspension, is not compact as an Alexander space, because it has quite a lot of maximal elements. Of course, more than infinite, more than finite, sorry. So this leads to a very nice theorem that says that an Alexandrov is a infinite product of Alexandrov spaces is compact if and only if all of them, but a finite number, have index greater than 1. So this is because of the maximal elements. Finally, we talk about the electoral systems modeled by Alexandrov spaces. An electoral system is a collection of two sets and a function. The set X is a finite set of options or candidates or parties or goods or something. E is a finite set of voters. And phi is what is called by Arrow and Chichelnitsky the aggregation rule. That is the rule to counting votes, basically. So an electoral preference, as it was called by Arrow, is a mapping from the set of voters on preordered sets where the underlying sets is the set of options. So as we saw before, a preord on X is also the same thing as an Alexandrov topology on X. So we can see an electoral preference as a mapping from the set of voters to the category of Alexandrov topologies on a given set X. And the aggregation rule is a continuous map phi from the set of electoral preferences to the electoral preferences. That is, a dictatorships on is an aggregation rule which is constant. So that's a topological definition of dictatorships. Now, finally, every compact Alexandrov space of index 1 is obviously connected. Now, more than that, an Alexandrov space of index 1 has the homotopy type of a constant, of a point, because the identity is less or equal than the constant map to x0 when x0 is the maximal element. And because of the previous exposition, the fact that a function is less or equal than another one means that f and y and g are homotopic maps. So the identity maps on X is homotopic to the constant map with the only value is the maximal elements. Thus, the poset Alex F, that is the poset given by inclusion of the Alexandrov topologies on a given set X, is a diamond-shaped Alexandrov space. So it has the homotopy type of a point. Finally, that gives you the resolution theorem by Chichelnitsky. That is, an aggregation rule, any aggregation rule is homotopic to a dictatorship. And that's everything I wanted to share with you. In my presentation, you can find all the references, and in the paper, you can find all the arguments and proofs that I did not give here. So thank you very much.
Thank you very much. Maybe one quick question, because still you are behind time, but maybe there is a question.
Please.
But there's not question. Maybe I will comment that Peter May was talking about Alexandrov spaces and finite topological spaces much earlier, of course, than he never was thinking about publishing this, because he thought that for a really famous homotopy theory person, one should not publish about finite topological spaces. But
Yes,
he was talking about this. And 2010, for example, he gave talk in Texas, and he said, okay, here's the 6-element space, and he wrote axioms. You can guess easily.
Well, his
Find
book,
homotopy groups of this.
his book called Finite Spaces and something else, I cannot remember the title, complete title, is on its way to the publication.
Ah, okay.
So we will
Very
have
good.
soon this book by Peter May.
Very good. Thank you. So now maybe very short break before the next stop, because we are late. So the speaker should prepare. Adrian Vasquez Marquez. Try to share.
Thank you very much. Nice to meet you. Bye.
Thank you. Thank you. Bye. And now, next speaker. Very good. So are you ready to talk?
Yes, can you hear me? Sorry.
Yes, now it's very good. So it's my pleasure to introduce the next speaker of this conference devoted to Zbyszek Oziewicz. And the speaker is Adrian Vasquez Marquez, and he will talk about parametric Hopf adjunctions. Welcome.
Yeah, can you see the slides?
The first one.
The first one, yeah, thanks. Just give me, that's it. Well, thanks very much for the organizers to accept my my talk. So I will talk to you about parametric Hopf adjunctions, and let's begin. Let's begin by the introduction. Consider the following commutative diagrams corresponding to liftings for a given closed monoidal category in a related monad. The first left diagram corresponds with a lifting of the monoidal structure for a monoidal category. And the right one, the right commutative diagram corresponds to the lifting of the closed structure for the monoidal category. Introduction. In 1981, Yeke-Moerdit characterized the lifting for a monoidal category using on-monoidal monads. In 2010, Bruguieris, Stephen Lack, Bier-Eliezer characterized the lifting for a closed monoidal category using a half monad. The objective in this talk, the objective is the following. In this talk, this last result will be extended to parametric adjunctions within a two-categorical structure. Why is that about this using a two-categorical structure? Because if you can see in 1981, the characterization for a monoidal category use a monoidal monad. What it means is that the lifting can be associated to a certain two-category of adjunctions. And the monad obviously can be related to a two-category of monad. If the two-category of adjunction and the two-category of monads are related, therefore we can say that the liftings in one two-category would be related with the two-category of monads, and that's more or less what we are going to do in this talk. So let's begin by defining the parametric adjunctions. If everyone is not very familiar with this concept. A parametric adjunction over P of the category P is denoted as J left adjoint to K over P, and is comprised of a pair of functions J and K with that domain in codomains, such that for every P in P, J of P is left adjoint to K of P with that domain in codomain. Let's begin by defining the two categorical contexts where we are going to leave these parametric adjunctions. The zero cells are adjunctions whose short notation will be left adjoint to R. The one cells are of type J, K, lambda, and rho with that domain and codomain. And the depiction, and its depiction is the following one, where J and K are functors, and we have lambda and rho. They are natural transformations. These natural transformations are called mates because they are related. And the natural transformation rho of J of K is asked to be an identity in these two categories. The two cells is a pair of the two cells are comprised of a pair of natural transformations alpha and beta with that domain and codomains, such that one of the following equivalent requirements is fulfilled. And well, these NS cells arrange themselves into two categories. For the two category of monads, what we have for N cells. For the zero cells, we have the monads. And the one cells are pairs of type J and C of J with that domain and codomain monads. In first I, we have a functor J. In the double I, we have a natural transformation C of J that is of that type, of the type of the diagram below. It's not a commutative diagram. It's just a diagram with a natural depicting the natural transformation C of J. This natural transformation C of J has to fulfill some conditions, some inequalities, and these conditions might be called the compatibility conditions with the multiplications of the monads and the units of the monads. These are the two equalities that are there. And the two cells, theta or theta for J to B, are just natural transformations. Theta shows that, such that the following diagram is commutative. The diagram below is commutative. That's well, we have defined the two category the two category domain and the two category codomain of the two adjunction that we are going to develop. For the left two functor phi of E, we have how does it operates on N cells. On zero cells of an adjunction, phi of E of the adjunction is the induced monads. On zero cells, JB operates those functor phi as J in lambda or R of lambda. And on two cells over the pair of two natural transformations, phi of E over the pair, it only takes the first entry. That's the definition of the left two adjoint over the N cells. The right two functor, the left two functor. The right two functor C of E is defined as follows. On zero cells, that is to say, the monad operates of the two functor over the monad operates as the field forgetful adjunction in the field forgetful function over the D'Alembert-Moore category, the D'Alembert-Moore category of the monad. On zero cells of the type P, C of P, with that domain and codomain monads, C of A over P, CP is a three entry, P and P hat and lambda of P and P hat. This one cell can be depicted as the diagram below. Since the natural transformation rho associated with this one cell is an identity, it says that P and P hat commutes with the right adjoints. That means is that P and P hat over the we can consider a lifting because it commutes with the forgetful functions. That's why is the concept of lifting for P and P hat, because they commute with the forgetful functions of the monads. On two cells, how does it operate the two functor is over theta xi of theta, it has to say xi of theta. C of E of theta is a pair theta and theta hat over the Dahlen-Bernoulli category is just the component of theta on M. So we have defined the codomain 2 category, the domain 2 category, the left 2 functor and the right 2 functor, and only remains to define the unit and the co-unit of the two adjunction. The component of the co-unit at an adjunction is a pair, is the identity over the domain category and the comparison functor for the adjunction. The component of the co-unit in a monad is just an identity in the two category of monads. Therefore, since we have a two adjunction, for every pair of objects, in particular an adjunction and a monad, we have a natural isomorphisms of categories of the type that is written at the bottom of the slide. I will leave you a couple of seconds for you to check it. And that's the natural isomorphism induced by the two adjunction. That's the two categorical adjunction context. So what we want to do is to have a lifting. Remember that in order to fulfill our objective, we had to lift a parametric adjunction, and we are going to do it right now in a very naive way for you to understand more or less what is happening. And for that, we have the following concept. A general lifting B of J can be considered as a one cell in the two category of adjunctions, as depicted in the diagram below. We say that B is a lifting of J, and remember the corresponding diagram for P and P hat. That would give you the connection. The obstacle that appears. Think for a moment that we want to, in a very naive way, we want to lift a parametric adjunction. So a proposed lifting of the parametric adjunction B left adjoint to W over Q for a parametric that would be a lifting for a parametric adjunction J left adjoint to K over P would be depicted as the following two diagrams. On the left, the lifting of B of J, and on the right, the lifting of W over K. But what happened? The diagram of the left is nothing happens with it. It lives is one cell in the two category of adjunction. But what will happen when the left one? The problem is the following one. If L tilde is left adjoint to R tilde, then if we take the opposite category, the opposite functors, the adjunction changes his direction. Therefore, if he changes the direction, is going to change the direction of the adjunction in one of the entrants. Therefore, if you consider the arrow that goes below, you are not longer considered only left adjoint. It's made of a right adjoint times a left adjoint. Therefore, that possible lifting W over K cannot live in the two categories of adjunction. Therefore, we have to define another concept of parametric adjunction in order to fulfill our objective. Therefore, we have to consider the concept more related with the parametric adjunction is obviously an adjunction. So we are going to consider adjoint object in the two category of adjunction. It might seem kind of a tongue twist, but it's not really a tongue twist. So we are going to consider adjoint objects in the two categories of adjunctions. For that, consider the following setup. A pair of classical adjunction, F left adjoint to G and H left adjoint to I. A one cell, consider also a one cell FH in lambda, depicted as the diagram below. Then the following statements are equivalent. Ji and lambda with the domain and codomain with that domain and codomain is a one cell, and there exists an adjoint object in the two categories of adjunction of the following type: FH lambda left adjoint to Ji lambda. That is equivalent to the following statement: lambda of H is invertible. In such a case, lambda of Ji is the mate on the inverse of the lambda Fh. Therefore, lambda of Ji might be called adjoint of lambda Fh, and is in the notation is written right next to the statement. As a note, we can say that H left adjoint to I might be seen as a lifted adjoint of F left adjoint to J. Definition: left J and B in lambda with that domain in codomain be a one cell in the two category of adjunction. A left half operator is another one cell. This operator operates over the one cell that we give, and H of J of B of lambda is J precomposed with a suitable R tilde. B is left undone, and H of lambda. But what is where H of lambda is given by the equality, but we can also consider H of lambda as the passing diagram, as the below passing diagram. That's it. Let's continue. Definition: one cell JB lambda with that domain in codomain in the two category of adjunction is a left half if and only if H of lambda is invertible. So for the following discussion, you have to remember the following context. We will have a one cell of type JB lambda with that domain in codomain, a pair of functions K and W in a pair of parametric adjunction, J left adjoint to K over P and B left adjoint to W over Q. So consider that setup. So if JB lambda is a left half one cell, therefore the following natural transformation is also invertible for all Q in Q. What we are doing is that we are passing on the left of the H lambda two natural identical transformations. So it's if the original one was invertible, the passing with the other one will be invertible, and the result will be denoted as the diagram below, and that will result in a natural invertible transformation. But before we establish our result, we have to give a note. If I have a parametric adjunction J left adjoint to K over P, therefore J precomposed with a suitable functor of tilde R is left adjoint to K of a suitable with a suitable precomposition of the functor R tilde over Q. That's it. So therefore, for any Q in Q, there exists adjunction. There exists. Well, remember what we have done is the following. For any Q in Q, there exists adjuncts of the form JRQ left adjoint to KRQ and BQ left adjoint to WQ, such that JRQ, BQ, and lambda is a one cell, and lambda or JBRQ is invertible. Therefore, using the result, we have an adjoint object in the two category of adjunctions of the following type, where that's a type where lambda of KW RQ is the adjoint of lambda JB RQ. Therefore, we have a kind of we have a theorem definition which says the following: consider a left half one self of that type JB lambda and parametric adjunction J left adjoint to K over P and B left adjoint to W over Q. Therefore, the following entries are one cells. I am not going to talk about too much about those entries, but the following are the following. I am not interested in the following ones. And for each Q and Q, an adjoint object JRQ, BQ, lambda is left adjoint to K R tilde Q, WQ. Therefore, this structure might be defined as a half parametric adjoint object and denoted as follows. Let's continue. We are going to define adjoint objects in the two category of monads. Consider an adjunction F left adjoint to G in F as part of the one cell as the following one cell, F C of F in the two categories of monads. Then the following assertions are equivalent. G can be extended to a one cell G C of G, and the following is then an adjoint object in the two categories of monads. F C of F left adjoint to G C of G. That assertion is equivalent to the following one. C of F is invertible. In such a case, C of G is the adjoint of C of F. That's the characterization of adjoint objects in the two categories of monads. This in the same way as before, in the similar way as before, we are going to give the following definition. Let J C of J be a one cell in the two categories of monads. The left operator H is another one cell. H of J C of J is a one cell, which is form of J precomposed with a suitable functor of the forgetful, and H of C of J, where H of C of A is given by the equality and also by the pasting diagram that is written depicted below. You can check it for a couple of seconds before passing to the following slide. That's it. So another definition: a one cell J C of J with that domain and codomain in the two categories of monads is a left of C if and only if H of C of J is invertible. So for the following discussion, remember the following. For the following discussion, remember this context: a one cell J C of J, a functor K of that type in a parametric adjunction J left adjoint to K over P. If we have J C of J as a one left of one cell, then the following is invertible for any Eilenberg-Moore algebra MKM, in the two categories of Eilenberg-Moore algebras. What we are doing also here is the following. We are passing a pair of natural identical transformations on the left. We are passing it to the H of C of J. So basically, that's also an invertible natural transformation, and the result is denoted as below. For that C of JM. We can give, previous to the discussion, we can give another note. If J is left adjoint to K over P, then J precomposed with a suitable functor is left adjoint to the key to K precomposed with another suitable functor. That would be parametric adjoint over P, over the two categories of algebras for the monad E. Therefore, for any Moore, returning to our discussion, therefore, for any Eilenberg-Moore algebra MKM, there exists adjunctions of type JM left adjoint to KM, such that JM, C of JM is a one cell and C of J is invertible. Therefore, using the result characterizing adjoint objects in the two categories of monads, there is an adjoint object in the two categories of monads of the following type. J of M, C of JM is the adjoint to KM, C of KM, where C of KM is the adjoint of C of JM. So we are going to give the following theorem. It's a theorem definition. Consider a left hop one cell of type J C of J in a parametric adjunction J left adjoint to K over P. Then we have two entries, and those two entries are one cells in the two categories of monads. I am not going to give too much time to those entries, but for the rest of the theorem. Continue. And for each MKM in the category of algebra Eilenberg-Moore, we have an adjoint object. JM C of JM is left adjoint to KM C of KM. Therefore, this structure might be defined as a Hoff parametric adjoint monad object and will be denoted as indicated below. I will give you a per second for you to have a look of the Hopf parametric adjoint mode that object just defined. Let's move on. Just as a note, the transformation, the natural transformation CK of UAE can be extended to a denatural transformation. This denatural transformation leads to an antipode, sigma of K. And sigma of K can be defined over P and D objects on the corresponding two categories as given by the equality. Since C of K UE was a one cell in the two categorical monads, reminiscent of the condition that has to fulfill that one cell, sigma of K fulfill the following two equations. And those two equations corresponds to the compatibility of this antipode with the multiplication of the involved monads, the first one. And the second is the compatibility of the antipode with the unit. It would be very interesting to check this result with the result of the article for Stephen Lack and company, because this equation, the equations that are in this slide are derived only because we are considering the context of the two category. Only because of that, we didn't deduce on any other context. Let's move on, and we are more or less about to finish. And don't forget the objective. We would like to leave parametric adjoint objects. Therefore, let's do a note in order to get the result. If I consider objects that are adjunctions given by free forgetful adjunction that are of the form free forgetful for one side, and for the other a monad, as for example as given at the top of this slide, I have an adjunction that is of the type free forgetful in a monad. If I do that, we can recall the isomorphism of categories derived for the two adjunction, and has the following type. The following characterization. We have an isomorphism of categories. Another note that we can give, if in particular I am using adjunctions that are free forgetful for a monad, in a monad, the adjunction given by the isomorphism of categories given by the two adjunction, this isomorphism is only given by the two functors, because the unit and co-unit of the two adjunction are identities. If I use a free forgetful adjunction and a monad as objects for the isomorphism categories. Therefore, remember, if using those objects, you only have to consider for the isomorphism categories the images of the functors C of E and phi of E and C of E. I can continue, therefore I can continue. So for one set of type J, B, and lambda that has in the left category for the isomorphism, and another one cell of type J, C of J, that is on the left category, being left half is preserved by the two functors. Remember, the isomorphism categories is given by the two functors. And the result that I am not writing it completely, but I'm just doing a comment, is that if you take one cell that is left, this left half property is preserved by phi on the one side. If you have a one cell that is half on the right, the functor CE preserves this left half property. So we can give therefore our objective can be fulfilled with the following theorem. Consider a parametric adjoint J left adjoint to K over P and monads and three monads, CS, DT, and PE. Therefore, there is an bijection with the following structures. Hoff parametric lifting of type J hat left adjoint to K hat over the category of Eilenberg-Moore algebras for the monad E, where J hat is a Hoff one cell in the two categories for the adjunction. This lifted parametric adjunction can make the following diagram commutatives. I will give you a couple of seconds to check these commutative diagrams. And I will give you one hint. Remember that the obstacle that was presented before, the only thing that you are doing in order to skip it, the great idea of Berlioz, Stephen Light and company, and the other one, I don't remember, was the following. You had to, in one of the entry, for example, take the commutative diagram on the left, and the forgetful function related with the monad E. What doing is just slide it to the K, and in that way you are only left with an identity monad, and preserve the forgetful function UT there. You have only to slide this. You have only to do this slide over the left entry of the right commutative diagram, and that would be it. If you understand that, you will get the result. It might take you some calculations, but you might get the result eventually. Yeah, sorry. This Hoff parametric lifting can be given a bijection with the Hoff parametric monad of that type. J precomposed with a suitable function of U with the forgetful function of E, H of C of E in left adjoint to the K precomposed with a suitable function with a suitable forgetful function. And that would be it. I don't know if you have any questions.
Time to end. Next talk is soon. So if there are any questions, let's thank you, speaker, first. And next speaker, the last speaker, should prepare his transparency so we can still ask some questions if you have. But if not, time for the next speaker because pretty late.
Okay, so yeah, so I'm the next.
Okay, so pretty late, so we should start now. So it's very nice to introduce the next speaker in this conference to memory of Zbigniew Owdziewicz and this Enrique. Do you pronounce Bojorquez?
Yeah, Bojorquez.
Bojorquez. Welcome.
Yeah. Thank you. Well, thank you very much. I'll do this quick and light. So the purpose of this talk is to talk about points and see an equivalence that happens in the commutative case, and then try to see like how it breaks in the non-commutative case. So first of all, what is a point? So Euclid said a point is that which has no parts. So that's what I'm going to start off with. That's as a concept of point. So first, well, we have the notion of a terminal object in a category C, which says that for every object in the category, there is a unique arrow that goes to that object. So if we're thinking about these arrows as some sort of like a figure of the type of the object in the domain, in the codomain object, then we're saying like this can be seen as a part of the codomain, right? So we're looking at X inside of one in this case. So if there is a unique arrow, well, one thing that we can see here is that if there is a retraction, then that means that if there is an arrow that goes back to X from 1 to X, such that when we compose them in this way, we get the identity, then that means that X is isomorphic to 1. So what that means is that there is, so when there is a retraction, it sort of is suggesting that this X figure in 1 is not non-degenerate, right? Like it sort of stays the same. It doesn't like collapses into something, right? So here we're saying like there's no non-degenerate, non-trivial X figures. Like if we see something inside one, it has to be one. Or it collapsed, that we cannot go back in a way that we get back the domain. So this kind of hint, like we could say like, okay, so then this terminal object is something that has no parts, because every part is the whole. So then this is our archetypical point, and we're going to understand the points of an object as the arrows that go from the terminal object to that object, right? So yeah, so this is our notion of points. So now we're gonna go and use Gelfand duality, which, so we take the category of compact Hausdorff topological spaces and continuous functions, and the category of commutative C-star algebras with unit and star morphisms. And well, the Gelfand duality states that there is an isomorphism. Well, this is wrong here. It should say the opposite category of one of them. So in like the category of compact Hausdorff topological spaces is equivalent to the opposite of the category of C-star commutative C-star algebras with unit. And this equivalence is given by two functors, which follow they're defined in the following way. So the one that is going from the category of topological spaces to C-star algebras takes each topological space and gives the set of continuous functions to the complex numbers. And then to each continuous functions, we're just going to, like if we have a function, continuous function that goes from X to Y, then the functor is going to, because it's a contravariant functor, we're going to the opposite category. Then what we're going to do is we're just going to compose first with F and then with G. So that's going to take a function from Y to the complex numbers to a function from X to the complex numbers. And the other more functor is very, very similar. So we take an C-star algebra, and we send it to the set of characters, which are the morphisms that are multiplicative and that they preserve the unit. So just like the star morphisms, well, the linear functionals, they go to the complex numbers. And same here. If we have an algebraic morphism from A to B, then the functor is going to, again, it's contravariant and it's pretty much the same. We're just precomposing by that arrow or morphism. So now the question is, okay, now we have this notion of what is a point, and so we can take the points of a topological space, which are these arrows that goes from a terminal object. In this category, a terminal object would be a unitary set. So yeah, a set that has just one point, and then we apply use the functor. We go to the category of C-star algebras, and here we can see. So we're gonna go. The terminal object is going to become the initial object in the other category, which is going to be like a set of complex numbers, and so we are going to go to a character. So points here algebraically can be seen as characters algebraically. Well, the points topologically correspond to these characters. So this is our new way of. This is our definition of point algebraically, and we can see that for every character, if we take the morphism going back, we're gonna go to a point of space. So now we have an algebraic definition of what is a point using the Gelfand duality, right? Which are again the characters, which are the multiplicative morphisms. Now, the states of a system. So if we suppose that X is the state space of a physical system, then what in reality, we don't really know what is the exact state of a system. We just know we have a probability of what the state is, right? When we're preparing something, we don't have like extreme precision, but we kind of know, yeah, like what is the probability of the state. So we can sort of course grain our view and then think of states instead of as points in this space, rather as probability measures over this over the state space. So this is like I call it like an epistemic state, because it's sort of, yeah, what we can know about the system. So we know probabilities about it, and yeah, and well, if we're in classical mechanics, we suppose that we can know with as much certainty, like it is epistemically possible, maybe we could say, or ontologically possible. So then to have a definition of state, like an abstract one, first we're going to use the Riesz-Markov-Kakutani theorem that says that if we have a topological space, a compact Hausdorff topological space, then every functional, so every linear functional that is positive in this sense. So yeah, if we take any function in the set of that goes from x to the complex numbers, and then we apply it f star f, and that's a positive number, and it's normalized, then there exists a unique probability measure over the space, such that applying this functional is equal to integrating over the whole space. Well, that functional with this measure. So this gives us a bijection between probability measures over the space and these functionals that are positive and normalized. So now we're going to have, this is a good definition for what a state is, like these broader like epistemic states in an algebra. So they're going to be positive normalized functionals, and the set of states, well, we'll denote it this way, and it's a compact and convex set with the star-weak topology. So by Krein-Milman theorem, we know that states that every compact and convex set can be seen as the convex whole, closed convex whole of its extremal points. And right now we'll just call the extremal points pure states, which are the states that have the minimum epistemic uncertainty. So are these states that now we know as much as we possibly could know about a system. And in the case where our algebra is commutative, or that is the same as that our algebra is a algebra of continuous functions over a topological space, then the pure states are going to be Dirac delta measures, which are like completely concentrated in one point. So again, we see that these measures correspond with points in the state space. Well, and so yeah, so what is the relationship between the characters, which was our first definition of a point, and these states or pure states, right? So first of all, a character is a functional, so it's linear and it's normalized, and the multiplicativity of the character implies that it is positive. So every character is a state. And well, now if we suppose that the character can be seen as the convex combination of two states, well, first we see that for every character, and if we have an Hermitian element, we're going to have this inequality, and using this inequality and the multiplicity of the character, we can do some calculations, and then we can see that we are going to end up with this equality, which is going to tell us that, well, because the Hermitian, it was for any Hermitian, so this is not always 0. So then this means that t had to be 0. I mean, t had to be 1 or 0. So that means that it had to be a pure state. So every character is going to be a pure state, and every delta measure is multiplicative. So in the commutative case, every pure state is going to be a character. So this is very nice because then, so we have that in the commutative case, there is an equivalence. We have two definitions, equivalent definitions of what is a point, and they correspond to these like points as arrows from the terminal object in the category of topological spaces. But now we have these two algebraic definitions. And now we're going to jump to the non-commutative case, which we called quantum because of the generalized uncertainty principle that tells us that if whenever we have this non-commutativity, we have an uncertainty principle. And so that is why we're calling it quantum, and the quantum refraction in a way, it's just like a poetic way of talking about how in the quantum examples, the equivalence breaks, which is what I want to show right now. So we're going to look at that phenomena in this example called the quantum sphere, which is the space. So again, we're doing quantum non-commutative geometry. So we're describing a space through a non-commutative algebra. In this case, we're going to use the algebra of matrices, 2x2 matrices with complex entries. And with this norm, with the supremum norm, this is a C-star algebra. And the group of symmetries of this algebra is SO3. So this is why one of the reasons we call it sphere and quantum, because it's non-commutative, and we're using Klein's philosophy that the space is characterized by its group of symmetries. So here we have, this is one of the reasons why we call it sphere, but we'll see that there is another reason. So now we have two ways of looking at the points of the space. So we can look at the points by like looking at the characters or by looking at the pure states. So what we're gonna do is we're going to put on lenses to see what are the characters. If we put these lenses and then look at the space, what are we going to see? So to see this, to calculate the characters of this algebra, we're going to look at the polymatrices, which are a base of this algebra, and they're very convenient because they satisfy these relationships that we have here. Like if all of them, like if we multiply them by themselves, we get the identity. And then if we commute them, we have the negative sign, and also that it's going to be the other one. Well, there's this like cyclicity there. Well, in this way with the imaginary number. So using this, first, let's suppose that we have a character. So then this character means that, well, because of the previous relationships, we are going to have that one, it's going to, well, the character is normalized, and then we have the square of each of the matrices, it's 1. So we're going to, and because of the multiplicativity of the character, we're going to have that their value is going to be different from 0. So it's going to be plus or minus 1, but the important thing is that it's non-zero. And the other relation will imply, like when we commute and we get the negative sign, well, this is going to mean that, okay, if I and j are different, then one of them had to be 0 because, well, these are going to be complex numbers, so, and they commute. So this is a contradiction. So here we have that the algebra has no character. So with these lenses, we're not going to see anything, or more precisely, we're going to see empty space. So now let's put on the state lenses and let's see how things look with this. So first, we can define an inner product this way with the trace. So we take two matrices and then we take the star of one, and well, we multiply them and get the trace. This is an inner product. So we can use Riesz representation theorem. that says that for every state, there is going to be a unique, well, for every functional, we're going to have a matrix such that this happens. So in particular, for every state, we're going to have this. And we want to, so we have a correspondence, right, from these functionals or from states right now. That's what we care about. And some types of matrices. And right now, just because this is very, it's very convenient and comfortable to use Dirac's bracket notation, I'm going to use it. So apologies for the people that are not used to this or don't know it. And I strongly suggest to know it. It's very nice. So using this notation, where we can see, it's not hard also to calculate that this is how these matrices are going to look like. This is their form, right? So we have an orthonormal basis, and then this is how they're going to look. And okay, so well, here we're going to define density matrix, because the idea is that these are density matrices. The matrices that are associated to the states of the algebra are going to be density matrices. And what we want to see is we want to know what these states look like, right? And we want to look at the space. And so we're going to look at these density matrices. There are positive semi-definite Hermitian operators of trace 1. Well, I mean operators, matrices. And then, so we're going to prove that these matrices given by the Riesz representation theorem are density matrices. So this is positive semi-definite. So if we take another vector, in this case, we are in the C2, and then we take this inner product, this is always going to be non-negative. So using, again, Dirac's notation, this is how we can represent our vector. And well, I know we're all tired and there's not a lot of time, so I'm just going to skim through this. These are the calculations. It's again, it's just a matter of seeing things as they are, and then just because we're on an orthonormal basis, this is why it's very comfortable, because a lot of things are going to go to 0, then 1, and eventually you'll see that this is going to be positive. Okay, and then, well, in every algebra, we have that a positive functional is going to satisfy this relation. So, well, with this, we can see that when we look at the ij coefficient of the matrix, which is this number, and then we apply this previous result, we're going to see that we are going to, it's going to flip. Like here, we can see that the matrix is going to be Hermitian. And so using this and that the state is normalized, we can calculate the trace of this matrix. So yeah, we can see that the trace is going to be 1. So, well, that's it. So this matrix is a density matrix, and then the idea is, well, for every density matrix, can we, like, does it correspond to a state? And the answer is yes. And how to do it is just the same way. So we take a matrix and then we define the functional this way, which is what we would expect and what we would want. And so again, the trace is linear, so this is a linear function. Because the trace, well, it's a density matrix, so the trace is 1. Then we're going to have that this functional is normalized. And well, because the multiplication of two positive operators is positive. The eigenvalues of a positive operator are non-negative, and the value of the trace is the same as the sum of the eigenvalues. Then using all of that, we can see, so here we're gonna have that applied to a positive operator, which has the form A star A multiply, well, this is the form of the positive operator. So we would take the trace of this, so the density matrix is positive, this other operator is positive, so it's all positive, and the trace, well, that means that the trace is, again, the sum of the eigenvalues, which are going to be non-negative, so this is going to be non-negative, so it's going to be positive. So this proves that it is a state as defined this way, and it's easy to see now that we have a bijection between the pure state and the density matrices. So this is good because now all we have to do to know what the pure states are in this algebra is to just if we know what the density matrices are. So, and this bijection is fine. So, which means that it's going to send the pure states to the extremal points of the density matrices. And so if we take another thing that is going to help us is if we take an orthonormal base of eigenvectors of a density matrix, then we can write it this way, which is like the diagonal form of it. And we're gonna have, because it's positive, then both of its eigenvalues are going to be positive, and the trace is 1. So we're going to have this sum. So that means that this is like convex sum of these two operators. And well, if it's a pure state, then it's going to be extremal. So one of these is going to be 0. So this is going to be the form of the pure states, like as a density matrix. So what we're seeing here is that the pure states are going to be one-dimensional projectors that have norm 1. Like we can make that association. So that's going to be very very useful. Okay, so yeah, we have this correspondence. So now we take a matrix. We're in a 2x2 matrices, so they're very easy to see. And if it's Hermitian with trace 1, then we can prove that this is going to be the shape. Well, this is how they're gonna look. So we're going to have 3 real values, well, variables, and then yeah, this is the form that the matrix is gonna take. And positivity means that the determinant is positive. So if we take the determinant of this matrix, we're gonna get this, and then this is equal, greater than or equal to 0. So that means that the density matrices are parameterized by the points of the ball of radius 1, the 3-dimensional ball, which is very, very cool. So now we can see that if we look at, well, actually, so if our notion of point is a little more relaxed, and instead of being the pure states, it would be just the states, what we would be looking at right now is a ball of radius 1. But that's not the case. We said that it's the pure states. So the pure states are, again, as we saw, there are these projectors, the dyads, which satisfy this relationship. They're one-dimensional projectors. So, and we have that the trace is 1. So the trace of the squared of the projector is going to be 1 as well. So we use this to calculate. So this is the square of the previous matrix. So we don't care what happens in these corners. We only care what happens in the diagonal. And we're gonna have that, yeah, this is 1. So this means that we're gonna get this equality, which is super cool. So now what are we seeing right now is that the pure states are parameterized by the sphere, the two-dimensional sphere. So when we put these pure state lenses, what we're going to see is we're going to see a sphere. So we have these two perspectives of, well, here it should be this of the matrices. So when we put on the character lenses, we won't see anything. When we put the state lenses or the pure state lenses, we will look at the sphere. So, well, this is a pun. So a space may seem pointless from a perspective, but that doesn't mean that it is from every perspective. And well, so before finishing, well, this suggests or make us reconsider what is a point, what is our notion of point, because then we have this classical way of seeing points as this that is something indivisible, and now like having this notion of pure state, that in quantum mechanics, like we know that we can't have these like delta measures, we don't have these points is classically conceived as this thing with maximum, well, because we said that points, pure states are these measures, probability measures with minimum uncertainty. So in the classical case, minimum uncertainty is going to be certainty. And now in the quantum case, it's not going to be certainty. There will still have uncertainty. So we do have some sort of indivisibility, which is what Euclid was aiming at. But this also looks very similar to the concept of monad that Leibniz talked about, because we have something that there is something inside, but we cannot see parts of it in a way. So it's like it's indivisible, but that doesn't mean that it is like empty. I don't know. The monads is also another concept that I still don't really understand, but it's sort of, I feel like this new notion of point as a pure state is closer to that than the point as just an element of a set. And well, yeah, so that's it. Thank you very much. That's my talk.
Thank you. Thank you very much. And are there any questions, comments? I see here some comment in chat.
What is the advantage of using category theory over set theory as a modern? Well, I guess like we could use set theory here. I think, but I don't know. I think that the notion of terminal object, I use category theory because I think that the notion of terminal object is captures more this concept of indivisibility. Like we could say, oh yeah, an element in set theory, but yeah, I don't know. I think it's just yeah, I have a bias because I like the categorical language, because it's talking about like we're defining things by how they relate to their environment, right? Like we're these universal definitions are, yeah, an object in relation to all the other objects within that context. And so yeah, I just wanted to use one of those definitions. But yeah, I won't have like a more concrete answer other than that.
So other questions, comments?
If there is time, just a couple of comments, very informal. I believe that the speaker has addressed some very fundamental issue. Let's go back in 1935, according to Einstein, Podolsky, Rosen, one of the biggest lack of completeness of quantum mechanics is locality, namely the definition of everything, all particles at isolated points, including Newton-Leibniz differential calculus, of course, potential, wave function, etc. That's why Einstein objected strongly against quantum entanglement. Back to your issue, you should know that in our recent, in the 2020 International Teleconference on the EPR argument, we did prove, you know, a weakening of the uncertainty principle whenever particles are properly represented as being extended, as well as think about proton and neutron in the nucleus. So not only you have extended charge distribution, but also you have in partial mutual penetration. So you have all sorts of non effect, non-linear, non-local. To make a long story short, I would like to, your talk is very closely related to mine on Friday morning. Friday night, there will be an open discussion. I would love to discuss with you. I'm too tired now to make any sense.
Yeah.
Perhaps to correspond, but your talk is very, you touched a fundamental issue. Indeed, thank you.
No, thank you very much. Yeah.
Thank you. Other comments or questions? Of course, will be time on Friday, as it was mentioned. So let's thank speaker again. And the session is closed, but maybe organizers would like to say something. I don't know.
Thank you very much to all of you for the participation. I think that the presentation for today show the high level of the work that Professor Osiewicz was doing, and it is very much comfortable to heard all your speaks. Thank you very much. And tomorrow we start at 9. The next section is with the name, excuse me a moment, Lie groups, symmetries, quantum groups, symmetries. Then we see you tomorrow, and I think that this conference is a great successful. Thank you very much.
I would like to say on behalf of all participants, I would like to say thank you, gracias, efkalisto, merci. Thank you for a magnificent organization, very hard work, and beautiful conference. Grazie, thank you, merci. In all languages. Okay, good night, everybody.
Good night. Thank
Good
you.
night.
Bye.
Prego.
Thank you.
Thank you.
Bye-bye. Buonanotte.
See you